2, bum. Klokken 9. 2. Se, den lyd her skal vi jo ikke have her i rummet.
There, and then they can sit behind without going across. This. But if it's here, then they can come in without going in front of the camera, maybe. Yeah, could make sense. So they can sit here, and if there's not enough room, then they can go over there. Yeah, you should have around 10 people. 10 people. Okay. Yeah. This one we can move it here. Maybe. Something like that. More behind. Yeah. How? A little bit more. It's more straight, right?
Let's try and see. Get any sound? Blah 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 blah. Just that's not the one or what? Two. Why is there no sound? Der er der så lyd. Why?
We can set it as a V shape, maybe, but it doesn't really matter. They will need to pass in front of the camera, and so it is. Worry about that.
Oh. So that's why. Danielle, can you log on the Zoom? Yeah, this one, but on phone or something, and just check if the sound goes.
Yeah, headphones. That's also why I want to have a second one. Then you have the.
So do you get any sound from my signal here through to you, or not? Nope. Which is a bit strange. What if we check out this one? Do we then still have it? Yes, we do.
I think Simon moved it.
Oh, okay, nice. So did this change?
Yes.
Yes, now you have my sound.
This is good.
Perfect. So this mic is for the speaker, but when people enter the room, that sound we have to get into this one. If people say something in Zoom,
Yeah.
people in here need to hear that, and that has to come from.
I can actually hear it. I don't know where you have the
Right,
microphone.
just still.
I can hear it.
Yeah.
So that's also good enough.
I don't think so because we're gonna turn up that sound because.
Okay. Then we can have the other microphone, the Tony Bolt.
Yeah, but I thought the microphone here for the people in this room.
Yes.
But when people on Zoom speak, we need to get, and that was my thought about the piano speakers. If we put them into that machine or this machine.
That one cannot make out the sound.
From Zoom, no.
Okay.
That sound is only from here and from the camera. What you say, what we say in this room.
No, yeah, but the sound of the TV, you cannot take the TV as an output. Because that's the way we used to do that. The TV, the sound of the TV.
From one of those computers.
This one.
Yeah, if we have a cable.
Which cable do you need?
Minitech.
Yeah, maybe if well, no, it has
Let me try.
I think the speakers from the piano is the best option. Could you get those, Matthias?
Yeah, speaks from piano
Yeah.
downstairs.
Yeah. Oh yeah, this one works. Maybe we should turn it down a little bit, like this, like this, like this, like this, so people in the room can now enter. Yeah, I think it works.
I hvert fald de ledninger der. Ja.
Danielle, try to say something in that microphone.
Hello, hello. Ja?
Yep. Say something in this room that people participating in Zoom.
Okay. So when people are, when the question comes from you.
Yeah.
Okay.
So make a lot of questions, because it needs to be work the system. Make a lot of questions.
Of course, there
You
will
are
be
the people in the room. Just in case.
nobody will be in the room or what?
We have
Question.
let's see, control for the TV.
Yeah, and the black one.
Okay. Shall I send the presentation to you, or how will we handle it?
Yes, USB and we put it in. USB and we put it in, I guess. But you are after the break, right?
Yeah. Yes, I do.
It's a normal. If you make it for then we.
Question was easy way. And you have them have it on the computer, and then I can make it possible.
Yeah, we put it in here.
And then I'll go from
Yes.
there.
And I put the clicker and then
Yeah,
we
we have one issue.
Yes.
See the monitor.
Yeah.
If you make a present, let's see, that's the presentation computer.
Nice. So what will it be on mine?
If we connect
Camera.
the output to that one,
I don't have HDMI.
to this one, but then we let's try. But then we cannot put the, then you have to put the presentation on Zoom via share screen.
Yeah.
To do so.
What do I miss?
And then, because, try to answer this. You can see,
Right on
and it's 9. So we can just start in a moment. You're welcome to take a seat. And then when if you need to have the camera focus on me, then you can just say Folkecenter here, and then pin, but then you need to unpin. No, that's this computer here.
Okay.
If you want this one here, this is the video from Nordic Folkecenter. No, not myself.
Okay.
So you just put here like this, and then pin. What is it? Choose filter, background, start, add pin. Never mind. Just run it without. But in general, you can block the picture on one speaker, so it doesn't switch when people are speaking. Then you need to take it off again. So let's not mess it up too much. So we have 14. Should we start the show? Are we good here with light? This? Yeah, perfect. Ready? Oh. So, good morning everyone, good afternoon, good evening, wherever you are in the world. We are happy that we have this 8th edition of our conference, and that so many of you that have joined in the previous years have decided to join again. We are aware of time zones limitations, so we know that there will be people coming in and out, and that's perfectly fine, of course. And if you miss any presentation, then they will all be available on our YouTube channel, which you will get also the link after all the presentation is over, all the material is over. Then you will get the link where to access the whole material. But otherwise, first of all, I would like to apologize for the delay with which you have received the program. But it has been a work in progress, which ended up pretty much this night. So I hope you can understand that. We don't seem to have any change in the program so far. Hopefully, we'll run it through. But if should there any change appear, then, well, worst case scenario, we have a little bit of networking, which is also nice. So the event today will run from 9 now to approximately 3:30, 4, depends on how long do we go on that. And that's Danish time, of course. And we will start with having some presentations from online speakers, and then continue with some in-presence speakers. So we'll have a blended approach. We don't have a big audience in presence this time, but our goal is that the 9 conference, which is going to take place next year in this period, will be as much physical event as possible. Of course, still live streaming, but we would really like to have people again to come to us and have a good discussions and good networking. So we will have a couple of breaks during the day, and there is a longer break, which is for us will be the lunch break. For people in the middle of the night, could be a good hour and a half of recovering the energies. And as said, we will finish around 3:30, 4. And then tomorrow we start again at this hour here, and we run a little shorter session. We will end up around 12:30, 1. So, without so many more words from my side, besides the welcome from Folkecenter and from the Danish Association for Small Wind Power, then we could like to move to the first speaker, who is Adrien Prévost. And he's a PhD candidate at the Ampere Laboratory in Lyon, in France. He focuses on the dimensioning and control of active conversion chain for small wind turbines. And he's also active member of the Wind Empowerment Association, of which we had presentations in some of the previous conferences. That means he is also involved in spreading knowledge in small wind technology and in running wind turbine workshops as well. Adrien, are you there? Hopefully.
Be on the list. The moment.
Of course, whenever you have a question, possibly not during the presentations, but right after, just raise your hand and then we will give you the floor, so that you turn on your camera, you turn on your microphone, welcome, and then you make the question, okay? So, do we have Adrien on board?
No.
No, not yet. So, well, that's a good start. But else, worst case scenario, then we can go to you as a second speaker, if it's okay. Yeah? We just wait a moment if he comes in. Maybe try to check the mail to see if he wrote something. No, there's not in yet. Well, then I guess we just move to Freddy. If you are ready for it, then...
I'm ready.
Yes, great. Then I will pass you over the microphone. So we will now welcome instead then Freddy Larsen from Thymøllen, Wind Power, who is a local manufacturer here in the area. And I'll just pass you over the microphone.
It's okay.
Thank you.
Thank you. Hello. My name is Freddy Larsen, and I'm sales manager for a company TWE Power. We are a local company who use small wind turbines. One of our owner, Fleming, made his first wind turbine back in 1975, which was made of things from an old car and what he else could find. He was very interesting. Just keep it. Okay. He was very interesting in wind power, and in 1984 to 5, the first really TWE wind power was set up, and some of this is still in operation in the region of TWE. So we can say it's a stable and a very strong wind turbine. Today we have more than 415 windmills around the country in Denmark. Our most popular wind turbine is 10 kilowatts. It's about 25 meters high, and the wings area is 40 square meters. It's also the most silent wind turbine on the market. and I will show you this so you can see how, I don't know, could I a little closer? Can you see it? Now see our wind turbine is there. Okay. Our 10 kilowatts wind turbine makes between 15 and 30,000 kilowatts per year, but we have also a few who makes 45,000 kilowatts a year. But they are standing very close to the west coast as England as nearest neighbors. The high energy prices, the 1.5 year, last year, has been a very win-win situation for us. And we sell about 1 and 2 windmills per month. Yes. Sorry. A typical custom is a family who lives in the countryside and use between 15 and 30,000 kilowatts per year with an electric car and ground heating or heat pump. We tell also our customers that they had to be very patient because it can take between 3 and 8 months to get a permission. Yes. So it was very short about us, and if you have some question, I'll hope my good friend Anker and me will do the best to do that. That was.
So if you have any question, just you can unmute yourself and ask. Otherwise, I have a question. Oh, go ahead.
I looked at your website. Your market is the Danish market, or are you also at other?
No, it's only the Danish market. We have no export.
Okay.
No, because the Danish market is very big for us.
Yeah.
Yes. So, yes.
How many wind turbines do they have running?
What?
How many wind turbines is running?
415 more than 415 turbines is operating.
Did you see an increase in the demand in the last year and a half? Energy prices that got up so much. Has there been more people wanting to have a wind turbine, or has
Yes. We can see about the last year there was a lot of people that were interesting. I think back in October, November, my phone is calling between 15 and 100 times in a week. Yes, every day. So it was very interesting, and it's coming again. We can see it's coming a little bit again. In the summer it was a little bit down, but now the winter is coming and the tariff is be higher than the So I think.
And have you been affected by the price of raw materials? That everything increased in the steel generators, all the components increased in price in the last year and a half. So have you been affected?
No. It's Anker. What? Yeah. Can you tell him that?
What?
About price increases.
Yeah.
Do we feel some? Is the wind turbine? Yes. I come again. The price for the steel price and the components is rising a bit, but the wind turbine is rising in price.
Yes, a little bit. Yes.
Okay.
Yes.
Do you plan to, at any point, to move to other markets, or is it Denmark the long-term?
No. we don't we have talked a little about it, but we don't think it's interesting for us because it's very expensive to get out in the world. So we had to be in Denmark.
The application process in from is the communalities or is it
Somehow it's easy because we don't have to pay for the cost to approve it, and they have a clear list what to do, but then there is a lot of bureaucracy. So no, it's not easy because they are a little in front of. You cannot just follow the European rules. They have some own ideas, and their own ideas is a little tricky.
We have a question from Shuru. You can mute yourself and ask. We cannot hear you. Yeah.
Yeah, we don't have a plan to change the design.
No.
No, this one is quite it's stable and it has run for a lot of years. So no, because then there need to be more selling.
Yes. Then
Yeah. So no, the market is not big enough to put extra money in there.
We work also on a hybrid system combination with integration with heat pumps.
It's not directly the wind turbine. I will come on some of that later today. I will talk about at the Folkecenter. I have two caps. I have Thymøllen and yeah, people know that. And it's a battery solution. Yes, I will come for that later. So when I begin to talk about batteries, it's not directly the wind turbine who do the job. It's more the combination how the wind turbine running together with the battery system. Yes, we work on that.
I'm a mechanical engineer and I also know that we build something and you use it, it needs some maintenance and you say we have a very reliable wind turbine. Was there a specific installation that you want to use and you have included in your system that is more robust or other reasons why you think this machine is so reliable?
Why we think it's reliable? I would say we have a lot of wind turbines running and they have been running in a lot of years. And we know there is a service every second year.
yes.
And when people keep this one up, and we can see how many of our wind turbines we have set up is running today. And I would say how many is running today of all the 450. How many is not running?
I don't know.
No, exactly. Because almost is, if someone move from their farm or want to sell it, then there is a market for used, and that's true. There is a market for used wind turbine we can see where people want to buy, and I would say is the price increase for the used. We are not directly involved in when people buying and selling in places and other places, but we can see there is a market.
Basic, was good design for the group itself.
I would say Freddy has the best answer when you try to sell. You are always asked people to visit some who have a wind turbine. Yeah.
And also, before you show the picture with the wind turbine and the noise level, but you will need to see the noise level. So if you could say what is it? So if you could say what it is compared to other machinery, because you have the chart there where Thymøllen is and where the other things are. Just the bottom part of the picture.
I have not.
No, I don't know. We have
No, we don't.
no.
Is
The
it?
bottom part of the picture.
Okay.
That one.
This one, but it's not compared with the other wind turbine. It's
No,
compared.
let's
Yeah.
It was.
It's just because we couldn't see the picture on the
Okay.
screen. So if you could say, when you take a Thymøllen and you compare with anything else, what is the noise level?
Then, it's easy if you can see it themselves more. Yeah.
Yes.
So Thymøllen is the plug here, the black box that you can see there, and that's how much is it? 14, around 45 decibel, right?
Yeah.
Yes.
So to make an understanding, the noise you have in an office it's around 65, and in a car is around 90. So that's giving you the level of how silent it is.
But if you go about 40 meters away from a Thymøllen, it's the same than you hear a dishwasher. Yes.
Are they displaced or don't they have this? Because you can see like there's a straight lift.
There is a twist. But you have to go closer to know it. But there is a twist. And this aerodynamic is it's old design. The blade is yeah. Many would say, oh, there's coming a new design. Yes. This one. Yeah. Who is though?
Any more questions from the audience? Hakan, are you there? Hakan Göçer Doried?
You're gonna.
And Adrien, you are also not there, right? So,
Okay.
thanks a lot to
Okay.
Freddy. Now, let's see. Oh, now I'm okay. Adrien, are you in? So whenever you're ready, you can just share the screen.
Hello, sorry for being late.
No problem. We just passed over to the following speaker. So I already made a presentation of you before. You can just share the screen and start your presentation. And welcome. Thanks for joining.
Okay, thank you. Can you see my screen?
Yes.
Okay. and the rotor diameter is from 1.2 to 6 meter, horizontal axis wind turbine. It uses a coreless axial flux permanent magnet generator, and in the most of the, in all cases, they use a passive diode bridge rectifier. The advantage of this wind turbine is that they have a lower levelized cost of energy than commercial machines, good performance at low wind speed, and it's open design, so it's very useful for studying small wind turbines as a scientist. And also it's easy to maintain because as it is open design and there is some courses about maintaining these turbines, then the local communities, they can maintain these turbines. So let's have a look on the global energy conversion chain. All these blocks here are the different elements of the wind turbines, and all the arrows, they represent either efforts or flows. So blades, bearings, permanent magnet, synchronous generator, rectifier, battery, they all interact with each other, and all have a role in the conversion chain. And if we model the efficiency of each of these elements, so the CP for the aerodynamic efficiency, the mechanical efficiency of the bearings, the electrical efficiency of the generator, and the electrical efficiency of the rectifier, all these efficiencies are related to losses. So as leverage to increase efficiency, we can play on some of these elements. So some are playing with airfall, rotor size, pitch of the blades. Some are playing on the topology of the parameters of the permanent magnet generator. It's possible to co-optimize these blades and generator together. It's possible to add some passive filters to adapt to match the impedance between the generator and the load. It's possible to adapt the DC voltage at the rectifier by interconnecting DC to DC converter, and then to have a sort of control of the torque of the wind turbine. It's also possible to change the nature of the rectifier, and this is the leverage that we have chosen. So we've chosen a controlled rectifier and apply some machine control techniques, namely field-oriented control. So here is the problem statement. Today, can we increase the energy yield of locally manufactured small wind turbines with a synchronous rectification strategy? So here is our approach. The goal is is to compare these two strategies with a fixed battery voltage and testing an identical generator with two different rectifying strategies, the passive rectifier and the synchronous rectifier. In the case of the synchronous rectifier, we need a controller because it is active. So we need some sensors to measure the currents of the lines, and also the position. We'll see later that it's possible to do it without the position with an adapted observer. So how to compare the different strategies? What comparison framework to implement? So we'll see that during the presentation. So let's consider the small wind turbine system. So we see the blades, the axial flux permanent magnets and generator, the currents, the rectifier, and the DC load. We have developed an active control strategies. And to test this control strategy, we have developed a wind turbine emulator. So basically what we did, we replaced the blade by a permanent magnet synchronous motor, which is controlled through a variable frequency drive. so that the torque of the blade is emulated, taking into account the inertia and the friction of the blade. I will not enter into detail, into more detail on how we did that, but you can, if you are interested, we have published a paper about this, and the reference is there. So we will use this tool to compare our strategies, and we will use the same generator. We'll see later that it might be a problem to use the exact same generator to compare both strategies. And then we compare the strategies, and this is what I'm presenting today. So here is the outline of the presentation. After this long introduction, we'll see the active rectification strategy. We'll say a few words about the experimental platform. We'll see the comparison frameworks. We'll show you some results, and then I will conclude with some perspective. So this is the system architecture. Here is the topology, an electrical representation of the topology. So this is the representation of the generator electrical representation, and this is the active rectifier with the transistors, which are controlled with duty cycles, PWM duty cycles. And here is a very basic view of the control scheme, which is composed of 3 layers. An MPPT algorithm. Here we use optimal torque control, which gives a torque set point that we control with field-oriented control by measuring the currents, the line currents, and the position of the rotor. So I'm talking about the angular position of the rotor, which is important to synchronize the currents with the position of the rotor to achieve a good control of the torque and optimal power factor. And this is transmitted to a PWM algorithm. Here we use space vector for PWM. Okay, so a little word about optimal torque control. It's a very well-known method, which is robust, tolerant to modeling and uncertainties, have high convergence properties. We use this law because of these reasons, and also because it's well adapted for small wind turbines, because it's small wind turbines, they have a low inertia, so it's and the main drawback of optimal torque control is kind of delay that can happen during wind transients and the torque response of the wind turbine. But in our case, it's attenuated by the fact that small wind turbines have a low inertia. So that's why we use this. I will not enter into more detail, but anyway, let's focus on this graph on the left. These are the torque curves of the wind turbine according to rotational velocity, okay, for several wind speeds. When using a passive rectifier, the intersection of the black line with the different torque curves gives the operating points of the wind turbine for each wind speed. As it can be seen, it is not possible to perfectly match the impedance. So it's not, in other words, it's not possible to match the optimal torque with a passive strategy. With optimal torque control, we will use this simple law. So this is the torque set point that will control with the field-oriented control to obtain the optimal torque. Note that here the optimal torque is the torque that leads to the optimal power, which is different to the maximum torque. Okay, because power is basically torque times velocity. Okay, and the gain, the torque gain K here, it can be either the theoretical aerodynamic optimal torque gain, which can be calculated with the maximum CP and the optimal lambda, and also the swept area, and also the rotor radius. But in fact, this does not take into account the losses in all the conversion chains. So we are not sure that we are sure that it does not lead to the optimal power. But anyway, we'll see that in the conversion chain later. So we can see in the conversion chain that if we control with the gain that maximizes the aerodynamic power, we are not sure that we maximize the DC power. So there might be another gain, which we call here KDC, that maximizes the electrical power. Okay. So here is the experimental platform that we use. So this is the real scale locally manufactured small wind turbine generator, axial flux. This is a torque meter to measure the torque on the shafts, and this is the synchronous motor that we use to control to emulate the torque of the blades. And this is all the instrumentation. So active load. We use a DSpace micro-like box to acquire the signals and also to control the rectifier. This is the VFD, and these are the two different rectifiers, the passive rectifiers here and the active rectifier here. It's difficult to see, but they are. So which comparison framework to use to compare both strategies, the passive one and the active one? Let's have a look into the voltage operating conditions of power transfer for both strategies. Okay, so let's define a ratio that we call M here, which is the ratio of the DC voltage divided by the amplitude of the phase voltage. Okay. For the diode rectification strategy, the power transfer can happen if this ratio is under the square root of 3. Otherwise, the diodes are not conducting. For the synchronous rectifier, if we want to use space vector modulation, that allows the maximum, that is the technique that allows the maximum voltage amplitude on the phase for sinusoidal voltage, then this ratio should be superior to a square root of 3, which means that these two ratios are not compatible, which means that if we want to use the same generator with the same operating points and the same DC voltage, it is not possible. Okay, so as in our framework we use the same generator, we will be constrained to use a different DC voltage to test both strategies. So this is what the remark here. With a single generator, it's not possible to compare the two solutions with the same battery. So that is one contribution of our work, is to clearly evidence that if we want to compare the two strategies, either we choose a fixed DC voltage and two different generators, okay, or either we choose the same generator and we have to adapt the DC voltage. Okay. So we have derived in our work an equation to find the adequate DC voltage for the synchronous at the synchronous rectifier for the optimal torque control load. Okay. So I will not enter into more details here. And for the diode rectifier, it is known that the impedance matching is sensitive to voltage. Okay, so we have taken for the experiment different DC voltage to simulate the fact that the battery could be discharged or at full capacity. We used simply the fixed DC voltage. We didn't use a complex model for modeling a battery, but that can be something that could be done on that test bench. Okay, so we've taken some voltages from 22 volt to 28 volts. So here is the experimental protocol. We've used the fixed steady wind. We've used like static power curve measurements. So we've measured from 3 to 10 meters per second. So we focused on the zone 2, which is maximum power point tracking zone. We've measured the voltage current at the DC side of the rectifier and the torque at the torque meter and the rotational velocity. So that allows us to have the electrical power, PDC, and the mechanical power, PMecha. Then we compute the efficiency, the aerodynamic coefficient, and the tip speed ratio lambda. Then this allows us to calculate a truncated annual energy prediction from a static power curve, which gives us an estimation of the energy that we could harvest with each strategy. Okay. Okay, so I will show you now the experimental results. Generator rectifier efficiency, we define it as I said, the ratio of the electrical power divided by the mechanical power. So here, the red cross, the blue cross, the red star, the yellow square, and the purple circle, they represent the different the tests that we've done with the diode rectifier for each fixed DC voltage. We can see that the efficiency is maximized around between 4 and 6 meters per second of wind, which means that the work of impedance matching was well done by the designer of the wind turbine. And then it vanishes a little bit, but it still stays good. As for the electronic rectifier, the active rectifier, synchronous rectifier, it's the blue and green and blue points over there, and they are systematically higher than for the passive rectifier. So, which means that we have a better efficiency for all the wind speeds with the synchronous rectification. Okay. Then let's have a look to the power curves. So for the synchronous rectification, we have a better power curve for all wind speed, but we can see that between 4 and 7, we still have good performance with the diode rectification, but the simple passive rectification is very sensitive to battery voltage. Okay, we can see that the impedance matching is good for a charged battery, but is not good for a discharged battery. Okay, so interestingly, discharged battery will tend not to charge. At least it will charge in a less efficient way than a charged battery, which is a paradox. Let's have a look now to annual energy production. Sorry. The two scenarios with active rectification are there, and all the scenarios with passive rectification are on the left. So from discharged battery to charged battery, we have increased from the annual energy production by 61% and by 19% for the minimum. We use the Rayleigh distribution at 5 meters per second average wind speed. I think that's all for the results. So now I will conclude. we've done a comparison of passive and active rectification for a 700 watt locally manufactured small wind turbine. Our experimental results show that the synchronous rectification strategy was more efficient than the passive rectification, and that the strategy led to increase the annual energy production by 19 to 61% in comparison to the passive diode rectifier method. We are working on some other aspects of the control strategy, which are adaptive maximum power point tracking, so finding which gain K of optimal torque control optimize the power output, but online. And we are also working on mechanical sensor-like vector control, and we have submitted a work for publication in this field. So now let's try to take a step back from this. Our research question is active rectification relevant to small wind turbines in the off-grid context? Obviously, it is a trade-off between efficiency, environmental impact, social impact, cost, complexity. It's not an easy question to answer, but what we are trying to do to answer this question is analyzing the robustness of our sensorless observer, because we are doing sensorless mechanical sensorless control, not to complexify the mechanical design, so to avoid the need of a mechanical sensor which measures the position of the rotor. We also conducted life cycle assessments of the system. We are also conducting some socio-technical studies. And as perspectives, we will design a specific generator adapted to synchronous rectification to make some co-optimization. We'll perform some field testing with a real wind turbine. And finally, we hope to be able to optimize with multi-criteria optimization the machine rectifier subsystem. I was really happy to present this work to some small wind turbine experts today, and I'm very interested to have your questions. So thank you for your attention, and I hope I was not too long. I didn't have a look at the time.
Working? Yeah. Thanks, Adrien, for the presentation. Is there any question from the audience, from the digital or from the physical audience? No? Not? Yeah? Yeah? Hey, yeah? And it will be a technical question, I'm sure.
Oh, how could you know it will be a technical question, Danielle? Yes, because it was quite interesting. You, Anker here from the Folkecenter, I'm a little more technical, as people maybe know. You was concentrated to find the right load on the generator and the refrigerator and the charts. It was very interesting. But what is your strategy in the controller in the real world? Because I could see you have made a test in the wind tunnel from 3.5 to 10 meter or something, 4 meter. But in the wind tunnel, you're supposed to run, so you will let the wind speed go from 2.5 meter to 8 meter in 3 seconds, and down again and up again. And as we know, is the rotor speed need to come up in speed, so it's compared with the wind speed. So if you have too much load on it, if you have full load on it, then it will probably take too long time. But what is your strategy to follow a quick up and down in the fluctuating wind where a small wind turbine is placed?
For your question, so, just a little precision, we have focused on the zone 2 between testing wind speed and wake wind speed, which is between 3 and 10 meter per second wind. But the wind is actually played by the motor, which is there on the left. So we emulate the torque of the blades with the motor. Okay. So we are not using a wind tunnel. So this is for your first question. And for your second question, with this emulator, we were able to inject some turbulent wind. Okay, we did not share this work in today, but if you have a look at the paper about the emulator, we were able to reproduce the turbulent torque that is applied on the blade thanks to the emulator, and we use the TurboSim from the Unreal to do that. And the strategy to control the generator, so to apply the torque on the generator, we use the optimal torque control. Okay, so we use the optimal torque control. I mentioned a very simplified 3-layer structure here. And this optimal torque control, the goal is to always apply a torque on the generator. So it's a negative torque because we are braking the generator, okay, which is proportional to the square of the rotational velocity of the wind turbine. And this particular law has a very powerful convergent properties, and which is very good for as a big wind turbine, but also small wind turbines, is that it enables smooth shaft loads, which is very important to limit the fatigue of the wind turbine. So, and why this? Because it uses the rotational velocity to compute that torque. I could go further, but maybe there are some other questions. I hope I have answered to your question.
Yes. Thank you. It was just you not killed the rotor. Okay.
Thank you. Any other question? Doesn't look like. No, sorry.
Have you done any estimation on how the cost would change of maintenance because you have added a switching component?
Thank you for your question. No, it's not for the moment. We are focused on the implementation of this. But we have not estimated. I think this is difficult to estimate this. Because we would need to perform some accelerated how to say aging of the components, and I think this is a bit tricky, and this is a whole domain in science to try to estimate that. But after a few years, maybe it's possible to determine how maintenance could increase. But it's very important question.
Yeah, thank you. So I think if there is nothing more, then we can move on. I would like to thank. Wait, there is a question here. Is the efficiency calculation, I guess, left out? Radius. Can you just ask the question in audio? Maybe it's a little bit clear.
Here, when we calculate efficiency, we take the electrical power at the rectifier output, and we divide it by the mechanical power measured on the shaft. So the shaft is over there. It's measured. The torque is measured by the torque meter. Okay. And the rotational velocity also. So what we basically take as efficiency is the electrical power that goes to the load divided by the mechanical power that is there. So it includes all the losses between the generator and the electronics rectifier. I hope
Thank you. So I would say if there are more questions, we can take it a little later, or you can just chat directly to Adrien. Just remember not to chat to everyone, just directly to him, so then you can get the questions. Or of course it can also be in the common chat, but then it pops up to everyone. It's a little distracting. So thank you very much, Adrien, for the presentation. So now we move to Hakan and Doried. We have a joint presentation from two former trainees of Folkecenter. As some of you might remember from last year's presentation that I delivered, we have a trainee program where trainees try to learn on as much practical way as possible renewable energies. And Hakan and Doried have been here, I think it was a year and a half ago, more or less. And they now graduated, and they actually graduated taking the project they started in Folkecenter, which was optimizing a blade of a wind turbine, and turning it into their bachelor project. I can see you are both here. I don't know who is going to start, how you're going to make the presentation, but now the floor is yours. Welcome, and welcome back.
Thank you. It's an honor for us to be here. Thank you inviting us for speaking about our project. Okay, hello, hi. Oh, nice to it. Doried was having trouble with his audio. I can see he fixed it now. Okay, during our internship at Folkecenter around 2 years ago, we picked a project called Make Your Own Small Wind Turbine. At that time, we didn't know anything about wind turbine and wind energy because we also didn't learn it in the university. Then in the Folkecenter, we make research, and we got help from people at Folkecenter. We took courses, like online courses, and then when we learned about how to make a wind turbine, then we said, okay, it's not enough, we need to do some research and development. And then we found that the noise is an issue, and also noise is also affecting the efficiency of the wind turbine blades. Yeah, that's why we made the research and development about the noise for the wind turbine blades. Okay. Next, please, do it. Okay, this was the our final prototype, which we made by our hands from wood, and we were testing this on the test field at the Folkecenter. Next, please. Okay, we would like to show you a few photos, like how we did it by hand. Here, first we started to designing in 3D CAD Inventor, and then we throw it on a plate, like raw material, and then yeah, we were removing most of the materials. Here you can see on the raw material, we draw the lines, we measured everything precisely, as precise as possible. Next, please. And yeah, here another photo. One is almost finished, and the other one is we didn't touch it yet. Next one, please. Okay, we use different kind of machines, like sand machine, to give it the shape better. Next one. Yeah, and we were also using hand sandpapers. Next one. And yeah, we checked the blades, the leading edge, especially if the blades were the same, precise. We found some mistakes, we corrected them again. And yeah, we coated the blades with epoxy with 5 layers.
to give them waterproof and to give them more strength. Yeah, at the end, it's quite funny because at the end we measured the total weight of 2 plates, and I don't know if you can see it, but both of them are exactly on the same weight. And that was quite awesome. Next one. Yeah, there was one wind turbine there, which was also made by hand. We removed the rotors and replaced our blades there. Next one. Here a short video of the blades. And there, when we were measuring the rotor efficiency after the calculations we made, but of course it was uncontrollable. It was not able to control the environment. But roughly, we got a 55% rotor efficiency. It was really high for 2-bladed wind turbines. Next one. Yeah, here we can see the CP, coefficient of performance of the wind turbine blades. If you look 2-bladed rotors, the maximum is 45%. And okay, in the calculations, we took some small consumptions. Even though, let's say, there's an error, I can say that it's at least 50% efficiency we achieved with those two-bladed wind turbine blades. Next, please. Yeah, then we took this into our bachelor project, and the noise is a real important issue. We also found some complaints from Siemens, and they say that numerous complaints have been made, and it can be annoying, sleeping disturbance, or even some people had health problems. That's why we wanted to work with this noise issue of the wind turbine blades. Here, Doried will talk. Yeah.
Hello, hi. Do you hear me clearly?
Yes.
Do you hear me?
Yes.
Yes. Yes. Yeah. Hi. And here I want to explain a short explanation about from where we get the noise, and we can see from this experiment that the noise comes from the end of the plates, and here the experiment put a mic here and sensor, and we can see that the red color is the high noise we get from the plates, and how the noise come from, and it is the air come turbulent boundary, and will generate in the trailing edge vertex, and vertex will make the noise. As I mentioned before, the tip vortex is the highest noise, and the noise depends on the trailing edge, and of course it's the point of the angle of attack. And there is this is of course a problem of the noise. It's a problem for the turbine plate, wind turbine, and there's many of existing solution. The first one is about design the plates, but the solution that's now it's used, it's after design there is a serration, which is this, and it's from Siemens, and improved by Siemens, and it will reduce the vortex and will reduce the turbulent number. And there's a campus technology with campus here between the triangle or between the serration here, and it will also reduce the turbulent boundary. And and there is a special coating which it's riblet coating which gets from the shark, and it's reduced 5 dB, and it is you can notice that serration reduced 7 dB, and the riblet coating it reduced 5 dB, and the compass technology reduced 2 dB max. All of the number are max. And you can speak Hakan here about which,
Yeah, when we were looking into the noise solutions and already existing, we also looked into other sectors, like rather than wind turbine industry. We found that in helicopter company called Airbus, they were also working on these noise issues, and they, as you can see, the plate is a little bit curved at the end. If you come to next slide, please. Yeah, and they were doing different experiments as well. With they made different plate designs, different shape. They were testing them, which one is best, and they found one of the curved ones best. It was reducing 5 EPNdB, and but they found that also the structure was quite weak. But then they improved the structure of the tip section, so it was suitable for flying in the helicopter, and they are using this in their helicopters right now. Next one. Okay, here we can see a clear photo of our design and a normal conventional straight wind turbine blade. But why we designed this one is because we also saw in other people, like in the helicopters, but we came with this design from nature, especially from birds. And why birds? Because birds are dealing with aerodynamics for thousands of years. They have their wing and size differently compatible with their environment. Each of them have a different wingspan and sizes, but we need to find a suitable one for our design. And we pick a bird which lives in ocean, and it was albatross. And the interesting thing is that their wingspan is up to 3.5 meters. And the blade we made was, one single blade was 1.2 meters. So total is 2.4 meters total wingspan. And they're known as gliders. They spend their life, most of the life in the ocean. And since they're known as gliders, it must tell us something, like they can glide in the air for a long time. So that means that they eliminate most of the vortexes, the air resistance. So when you also eliminate those issues, then it should also make less noise. And then we make our designs in Inventor like that, one with straight blade. We also tried with the blue edge blade design, like we try to make similar to that one, but in the further slides we will not talk about that one. We will only compare conventional and the curved tip blade design we made. They're at the same size, I need to mention, and the same diameter. Yeah. So now he will talk.
Yeah. And you mean the same size or different? It's a curve.
No, I meant the same diameter.
Yeah. And it was our project, our final project in university. So we print our plates, which it's straight and blue edge and curved plates. We printed on 3D printer, and after that we ensure that it's the same. Our plate, it's our turbine, it's 2 plates, and so we ensure that it's perfect. And we make our simple test, simple lab to get to know if it is which is better, and to know more about curved and straight plates. And the first test was about to calculate to know how much noise we have. So we bring voltmeter, mounting bracket, and dB application to measure the noise by mobile, and our 3 type of plates. As Hakan said, that's we have 3 type of plate, but to don't confuse you, we here explain only about 2 plates, the straight one and the curved one. We don't want to speak about each blue edge. And as a result, what we did here, that's we let the plate smooth, and we calculate, we put the microphone here, and there is here plates, but here it's not shown because it's very fast. So the tip of the plate here will get the max noise. So we will have how much dB we have. So after calculation, there is here how many volt, and here how many noise. So we start at 1 volt, and we finish at 6 volt. And here we can notice that the straight plates has more noise from the curved plates, especially in when we in 2 volts. The difference it's less 14% less than the straight plates, which is good. And after that we make power consumption, the same tools, but we want to know how much every plates consume, and also there is a volt here, and there is a power here. And when the difference here, we can see that also the straight plates use here more power more than our design plates. And here in the 4 volt, there is a gap like 29% less than the straight plates, which also very good. And we want to make how generate the power, and we use it another tools. There is here put a van here, and the van there is a distance. Put the turbine here, or small turbine here, and the voltmeter device, and the van with distance. The first test is for example 10 centimeter. The second test is 20 centimeter, which will get our turbine will get different wind speed. And we have anemometer, and we use our plates. And here we want to show you only 2 distance. The fan far away from our router with 15 centimeter and 30 centimeter. Of course, everyone has different wind speed. We can, as here it's volt, the volt for the diagram, and here it is it's a time, and we can see that the curved one, the orange one is the curved one. It's our design, and it's a start from 2.5 almost, and the straight one starts 3.5 seconds. So the curved one starts generate electricity, started electricity from before the curved one. And if you also we make the van far away, more than 13 centimeter, and also we have a very good result that our design started from 2.5 seconds, and the straight one started from 6 seconds, which is better, or curved it's better, and the rest of the curved is by experiment it's better than the straight. And after that we analyze it by ANSYS, and as calculation here, that we can see the straight place design for max von Mises stress is the best, and it's logically because it's straight, and maybe here there's thicker than the curved, and the curved plate is 15, and if we compare it's okay, because our calculation it's the number must be under 30 megapascal. So it is good to work, and it's okay if we compare with another plates. As a conclusion, we are so proud for that we succeed to have a very good result, and to decrease the noise and increase the efficiency, and we want to develop it. Maybe it's as we can develop it by making achievement and optimization design shape using fluid design, and we can improve of test corrosion, improvement of testing, corrosion evaluation, and maybe structure optimization, and we can combining with existing solution, which I spoke before, serration and coaching and outcomes. We can put it on the plates, so maybe will be reduce the noise more. Thank you very much, and I was very happy to present this presentation, and any questions you are ready to ask.
Thank you, Doried and Hakan. Very interesting project indeed. Is there any question from the audience? From the digital audience? Well, if it is, then you can always write in the chat. Oh, yeah, there is one. No, okay. So, thank you very much. If you have any question, you can always ask them to them as well. So now I would suggest to have a 10 minutes break. We are running a little behind the schedule, but we just need to set up a couple of presentations coming in now. And then the next presentation will be a physical presentation from here, from Otto Reinke. So we see each other in 10 minutes, which should be 10:30 our time. It's your turn. Yeah, now. Yes. And just ring the bell.
Okay.
Ready?
Nope. We have to wait as the others are coming, or? We're working soon?
No, we go.
Okay.
Yeah, so welcome back. Now we are a little behind the schedule, but no, actually perfectly back to what it should be. So it's a pleasure to have here Otto Reinke, who has been testing with us for quite some time now, and you know him already from previous presentations, but now he has a product that good
Okay.
to present, right?
Okay,
So,
great introduction. Thank you, Daniel. Okay, as Daniel has already mentioned, I'm quite close to the Folkecenter since a couple of years, and we have done quite an interesting journey together, and today I will show you a little bit where we as Tandem Wind Energy are located and how far we are at the moment with our product. You have to show me my presentation, then I can show you something. Okay. Yeah? Perfect. Mm-hmm. Nope. 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 Okay, now it works. Okay, normally we always start with a kind of vision or what we are believing. So as Tandem Wind Energy, we think that the energy system of the future will be to a largest extent decentral, renewable, autonomous, and it will be small. It will be a combination of photovoltaic systems and small wind turbines, and they will have their place in the market for in the future. This will be for sure. We as Tandem Wind Energy have started a couple of years ago with the development of our small wind turbine, but it has not started from scratch. We have taken over the basic development, which has been done by some companies in Germany called SMA, Solar Technology, from Airdyne in Rendsburg and from ISET in University in Kassel. So they have created the basic development for the small wind turbines. We took it over, and then we have started the redevelopment of this concept. In the end, in our starting point was the following. You see here where we have installed the first wind turbine here at the Folkecenter. At that time, we have a small wind turbine, 5 kV, horizontal axis, with passive stall and with which was a downwind concept. And we were using pultruded rotor blades. That means we have a rotor blade which is designed in two dimensions, in two directions, without any twist. It was, in terms of production cost, quite impressive, I have to say. But we were facing some problems with it, and therefore we have to completely renew the development. We were starting with the machine unit. The basic idea has not been changed at that time. The basic idea was we want to have a single frame housing like we have in the automotive industry. We want to have an easy commissioning and easy exchange of the product. And we want to have a protection against external media, corrosion, and so on. And therefore, we have adopted this concept, which has been developed by this group of companies before. And we were looking for a good supplier to create this or to bring this idea to reality. With them, we developed a new bearing concept. We have a new RPM measurement concept. The brake system has been completely reworked, and also the safety chain with centrifugal switches, temperature switches, and vibration switch have been completely new installed for this concept. The next one was then, the next challenge was then to make a redevelopment of the controller concept. The previous one was a complete new project, and we had to replace new functions inside, like control functions as well as monitoring functions. Reactive power control we have integrated. Of course, the VDE concepts in a lot of countries, the requirements for grid protection have been raised, so therefore also we have to take this one into account within the development. And we used also standard components in order to secure an easy to repair process. And of course also remote system monitoring and parameter change we could also realize with this product now. One challenge was definitely the downwind concept. The downwind concept itself it's great because you need no wind vane. The wind turbine is always orientating itself to the wind. It's great. But the big challenge and the big problem was noise. Because the wind is always coming first through the tower, and then going on and then it's creating wakes. And the wind turbine, the rotor blade is always cutting into the blade, into the wakes. So therefore we tried really a lot of things in order to optimize this concept, but this was not possible. Afterwards, finally, we decided to make an upwind concept out of it. What we have done is we have, for this downwind concept, we have tested different rotor blades. We have 5 different rotor blade profiles tested it. We had pultruded rotor blades. We had twisted rotor blades. We have made simulations, field tests, different cone angles, tilt angles. We did really a lot. We also used different materials. But as mentioned, we could not get rid of the noise in a downwind configuration. So therefore, we make an upwind. It was a lot of work, not only in order to find the right profile, but also in order to fulfill the requirements for testing it. So especially here for this rotor blade has a length of 2.5 meter, and we have to have some testing requirements, the classical way. So we had to put 200 kilos on this rotor blade on 2/3 of the length of the blade, and it has to survive without breaking. So, and this was done in the end very successfully. We have now 2 rotor blades materials. We have this rotor blade profile in wood as well as in glass fiber, and both have passed successfully this testing. Then we had when we create an upwind wind turbine, we have to see what is necessary in order to steer it to the wind. The classical way was to have it in a kind of, with a wind vane. Also this one we have tested, but this was not successfully at that time, because due to the load on the wind vane in the end, there was so much load on it that we had faced problems to fix it on the current machine housing. And therefore we have decided, no, we will go in a different way. We will put there a yawing motor. So we are very unique, I would say, in the 5 kV segment of small wind turbines, using a yawing motor in order to steer the wind turbine optimal to the wind. That means we have an anemometer system, we are measuring wind direction, wind speed, the information goes to the controller, and then we align the wind turbine optimal to the wind. Other challenges are also the lattice tower. Our idea was always to have a wind turbine which we can erect without a crane. So we have standardized modules of 3 meter, and we can configure a 12-meter tower, a freestanding 12-meter tower, and an 80-meter guide tower with this configuration. It is like a telescope concept. We can put the elements inside. We have a length of 3 meters roundabout, and we can transport it very easy with a trailer and a car. We can transport the whole small wind turbine wherever we want to. Due to the yawing motor, we also had to change the design. We tried a lot of different projects. In the end, we came to the bubble or to a ball design. So Enercon has his egg, we have the ball, and it has some very good possibilities to make also to individualize it. The nacelle cell itself is a fiberglass housing, and which is protecting, of course, then the machinery, and to the machinery itself. But also we are planning to have customized designs. You see it here at the moment on the right hand side, a little bit like a Pokemon. You see it in the top right. Or we can also have a kind of art edition. People were also coming and saying, we like to have it with the Earth, in form of an Earth. We say, okay, it's no problem. And there are also some coming from Star Wars and say, we want to have the Death Star in this design shape. Okay, it's a little bit challenging, but we are used to it. So in the end, we have now a product, 5 kV horizontal exit upwind passive stall active yawing system, 2-stage induction generator, 3-phase, 50 Hertz, 400 volt. So that is where we are now. But we also talk about partnerships today. And to create this product was not possible with strong partnerships. A lot of this development we have done here with the Folkecenter, where we have in the meantime a very good and very familiar relationship, I have to say. And the focus was here in the rotor blade, the yawing system and the controller. Currently we are working also on the duration testing, the safety and control testing and noise testing, which we need here for the certification process for the Danish market. Partnerships for the development, production and development. I'm always a friend of using the competence of people who really are strong in a certain field. So I involved in the beginning of the development process also already my suppliers. So in total, and you show it in the end, I have 5 strategic suppliers for the whole wind turbine. And with them, I have developed and optimized the different products. The advantage is for me, I have access to industrial production and know-how. I can save investments in productions because as a startup, you can imagine, you cannot invest so much money into a production facility. We can increase competitiveness and flexibility because the dynamic, especially in the beginning, the dynamic of the market, I can shift to my suppliers. And I can reduce, of course, my high fixed cost. So therefore, you see here, this is a little bit to visualize partnerships for the nacelle, for the machinery, for the tower, for the controller, for the design, for the nacelle housing, and for the rotor blade. And in the end, I press a button, I get 5 packages, and my wind turbine is ready. And aside, of course, we have also the know-how carrier with the Folkecenter. We're also using here the competence of Groningen, of the Hanse Hogeschool, and also of the Hochschule Emden-Lehr in Germany. In the meantime, with these guys, we're also preparing a new project, which hopefully will start in spring next year. So references to I have erected, one is here at the Folkecenter, the other one is in Germany. We have erected, and now we are starting to make to start with the market entry and with the sales, because in the end, the small product has to find the way into the market. Target groups are, as a lot of you also know, agriculture, commercial industry, public facilities, private households, and we're also using small wind turbines as an advertising medium, because if you see what does it cost to have a billboard for 20 years, maybe this is also a better alternative, because you can also create some energy out of it. How will it see? CI branding. There are some examples how we can create also our small wind turbine. For example, adding different logos or logos of companies to these wind turbine. Next step will be definitely we are looking for partners. As I mentioned, we have finalized the development and the production facility, everything is prepared. Now we are looking also for sales partners because especially in the international content, local partners are always best to enter a market because they know the language, they have the experience, they have the context to the different people. So therefore we are looking for partnerships in different countries, and the idea is to provide them a possibility to expand their existing portfolio. For example, people have already one wind turbine, or they are already in the photovoltaic segment, or they are working with storage devices. Maybe they are interested in adding a product like a small wind turbine to their assortment. And they should have experience with the installation of wind turbines. We, of course, will support them. We will train them, give them technical advice and technical support. As I mentioned also in the solar and storage sector, this is the companies we are looking for in the next steps. So that is a little bit an overview of the journey we have made here, also together here with the people from the Focus Center, where we are now, and now is the next challenge. It will be the market entry. So thank you very much for your attendance and for listening. If you have questions, you're welcome. Thanks.
Thank you, Otto. So we have one question from Ignacio. Just go ahead, Ignacio, unmute yourself.
Well, the cost of, well, you have two possibilities to calculate it. On the one hand, sorry? Okay. On the one hand, you can calculate the return on investment on a product. On the other hand, you can also calculate it, what does me a kilowatt cost. This is depending on the different locations. You know, if you have a low wind area, you maybe create only 4,000 kilowatt hours per year. If you're on the coastal side or on a very good situation, you can create up to 10,000 kilowatt hours. So if you want to have a profitability analysis, you have to know the environment you are working in. In principle, I have to say, photovoltaic is, as of today, unbeatable in terms of cost of energy production. It's a matter of fact, we cannot ignore it. But a lot of people who have their photovoltaic installed as of today, and now we are in September, October, they feel very quickly that the energy production via photovoltaic is going down. And then we come with the strength of the small wind turbines. Because this gap in autumn and winter, we can close with our wind turbines. And say, now we can support you in securing the energy availability also in this period. So in the end, it will be, the optimized structure will be always a hybrid system, having photovoltaic, having small wind turbine, having a storage behind, and then balancing the differences in day and night and summer and winter. That would be the optimal structure. I hope I could answer you a little bit the question you're asking for. Sorry?
It looks you answered. Yeah. If he's not complaining, I guess it's okay.
Okay.
Other questions from the audience? Otherwise, which countries are you targeting?
We are starting here at the moment here in Northern Europe, but then we want to expand to South Europe. We had recently got a request for Australia. It depends really on what kind of customer is contacting us or wants to make a partnership with us. It depends a little bit on the countryside and the requirements of the countryside. So for example, in Denmark, we are at the moment preparing the certification, which is necessary in order to enter the market. Other countries is less complicated, like Netherlands, that is easier to go in these countries. Or we have to, like say, the US market. It's interesting because they have very good environment at the moment for starting in the US, but technical requirements has to be adapted, so that will be a second step or a third step. We start in Northern Europe, and then it depends on the partner who is coming to us, and based on the discussion which we are following.
And then we have a question from Robert. What is the cost of the system?
That depends on where the customer is living and what kind of market price is possible. At the moment, I have to say, we have some projects running in Germany, but in the end, it has to be country by country. It will be evaluated. Because, you know, we have done a two-step distribution, a business to business concept, and we have to come from the market, and we have to come from the cost price, and then in between, two partners have to be happy with that. So this is really depending by country.
Yes, and Juande, yes, it will be you now. Just there was a question related to next presentation.
Okay.
So thank you very much, Otto.
Thank you.
It's a pleasure to have you also present here. So our next speaker is Juande Bornay from Bornay Wind Turbines in Spain, and they have quite some experience in the sector, because their first turbine, from what I could see from the webpage, dates back to 1970. And on top of that, they are also selling wind and solar and other systems included. So they sell an ecosystem. So maybe we can also hear a little bit from them how it is going with the competition with PVs, which in Spain is really, really tough. So Juande, can you, oh, if you need to stop sharing the screen here. So I saw he's online and he wrote. See. Yeah, perfect. Now we can see the screen. Welcome to our conference.
Thanks a lot for your invitation, and of course, as you say, we are present in the small wind turbines. We manufacture small wind turbines since 1970, but since 2005 we are also in the distribution market, selling solar modules and other products like inverters, chargers, batteries, etc. So we have a few experience in both markets. And of course, as you say, in Spain, we have a big boom during the last year. This year is not so big, but we can compare and we can talk a little bit about solar and wind. In my case, of course, as I told you, we start the project to produce small wind turbines or to produce energy with the wind speed in 1970. My father, in this case, is who started with this project. We have more than 50 years of experience, and we say that allow us to improve the life of the different users. At Bornay, we produce 100% of the wind turbines in Spain. We have different sections like raw materials, raw materials, that is input of the material into the company. We have three main sections, that is mechanical, electricity and composites. At the mechanical section we produce all the mechanical parts, stainless steel, iron, coppers, etc. enters, and we prepare the different parts. At the electricity department we make the windings and the controllers, and the composite section is where we produce the blades, tails and the different parts that protect the wind turbine. From these three main sections we go to the assembly, and then we assemble the wind turbine. After we assemble or we make the wind turbine, we go to quality and we make different tests. Mainly we test the alternators, we check that the power curve, power, voltage, etc. is okay and according with the specifications. We test the control boxes, the regulators and the interface, and then when all this is ready and we have checked that the quality is what we are selling, or we told that we are selling, then we prepare for delivery. We also have R&D department, research and development department, that is formed by different persons of the company, and we normally supply with solutions or improvements to improve the wind turbine. Along these more than 53 years of experience, we have done many developments. Of course, in 1970, we start with the first wind turbine. In 1978, we produced some parts in fiberglass. In 1982, we introduced the induction alternator, but this was not a good solution because we need to accelerate the wind turbine and then make the induction and start to produce. But in low wind speed, the wind turbine was not producing. So this is not a good solution. In 1984, we introduced nylon injected blades. This is a very good and robust solution, but for small blades. If we are talking about 250, 500 or 600, 700 watts wind turbines, this is a very good solution, cheap, fast to produce and very heavy, but not nice solution for bigger wind turbines because the weight is too much and we have other problems with mechanical parts. In 1988, we introduced permanent magnet alternator and pitch controlling to the blades. We increased the production of the energy production of the wind turbines, and with the pitch control, we introduced one very nice part that is control, the RPMs control the pitch, the torque of the wind turbine, but with a very expensive part, a mechanical part with different parts that also increase the maintenance levels of the wind turbine. We consider that this is not a good solution. In 1993, we start to produce fiberglass and carbon fiber blades, especially because we was increasing the power of the wind turbines up to 3 kilowatts, and after more years, we also produce 5 kilowatts. This means that we can produce larger blades with lower weight and stronger. In 1997, we introduced the neodymium magnets. We changed ferrite magnets in our alternators by neodymium, and this increased between 15 to 30%, depending of the model, the power production. In 2000, we changed the method to produce the blades, and we introduced RTM, resin transfer molding. There is the same result, same fiberglass carbon fiber, but we accelerate the production. Until the RTM introduction, we was producing one blade per day and mold, and after we introduced RTM, we was producing one blade per mold an hour. So we multiplied by 8 the production of the blades in only one shift. This is a big advantage for us because we can accelerate production, we can reduce price, and we keep same quality and same characteristics of the blades. In 2008, we start to produce grid-connected systems, and in 2018, we introduced Wind Plus. That is a very, for us, is a very advanced into our production of the wind turbines. As we say, Wind Plus is one step ahead in small wind turbines, and I will explain why. Until Wind Plus, we was producing 16 different models with 7 controls for only 2 applications. We have 2 wind turbines, 600, 1.5, 3, and 6 kilowatt for 2 applications, battery charge or grid connection, with different windings, 12 volts, 24 volts, 48 volts, 120, and 220. For example, in case of certification, this means that we need to certificate 16 different applications, 16 different models. This is too expensive for the market that small wind turbines have in this moment, so we need to search for different evolutions. With the Wind Plus, we have 3 models, 3 only alternators, 1 kilowatt, 3 and 5 kilowatts, with a 220 volts AC output, using for 2 different applications or 2 different controls, MPPT charge for battery charge, and a standard model that can be applied to 12, 24 or 48 volts, and one interface that can be used for different applications like grid connections, water pumping, or telecom. So finally we have 3 models, 3 only windings, with 2 controls for many applications. So we reduce from 16 different windings to only 3, and 7 controls to only 2. So this increase a little bit the production of the models and reduce a little bit the cost of the production. In this case, the Wind Plus is composed by 3 models, 13 plus, 25.2 plus, and 25.3 plus. This means 1, 3, and 5 kilowatts. 2 control boxes, that is MPPT charge controller and interface, and applications for battery charge at 12, 24, 40 volts, grid connected, water pumping, telecom, or other applications. You can see the models and the control boxes. The MPPT charge controller is only 1 box, but the interface we can show in 2 different configurations. It's a box to put into the wall, or we have an interface for telecom applications that is rack format. Which are the most important improvements in these cases? We have a new unique alternator, 220 volts, not 20 as shown in the presentation, 220 volts AC. We reduce the cost because we are producing only 3 alternators. All the windings are exactly the same. We have increased, or we have a better performance. We have a better cut-in wind speed. We increase the efficiency up to 96%, and we have a better control of the wind turbine thanks to the controllers. That, as we see in a previous presentation, we are working in active torque control. We control the wind turbine by amperage, voltage, or RPMs. We have 3 different models, 1 kilowatt at approximately 12 meters per second, 3 kilowatts, and 5 kilowatts, always at 12 meters per second. In this case, the MPPT charge controller is also a unique model. We have 20 to 220 volts input coming from wind turbine, and we have output to 12, 24, or 48 volts. We have a limit output to 125 amps. We can use any kind of batteries, loaded, AGM, gel, lithium, etc. We have a functionality without batteries. It means that if we disconnect the battery, we have an MPPT track control with self-learning algorithm. It means that depending of the place that we have installed the wind turbine, the power curve, depending of the humidity, the pressure, etc., can change a little bit, and the controller will learn for himself and improve the power curve. As we see previously with the presentation we have from one colleague, we can increase, or we have increased the production of our wind turbines by 20% by applying the active control of the wind turbine. We can also introduce a quiet mode that we can program this mode in, for example, when we are using in an urban area or windy area, or there is a big storm, hurricane, etc. coming, then we can program a safe mode or quiet mode that reduce the RPMs and keep the wind turbine in a safe mode. We have removed displays or LEDs, etc. that we have previously, and we introduce an internal server with Modbus communication that we can communicate through to internet or to other applications to show all the information of the wind turbine. We have different input signals and auxiliary relays. We have 2 auxiliary relays to control different applications like BMS from batteries, or wind speed anemometer, external temperature, external options. In this case, there is the interface that is similar to the MPPT charge controller, but we can have in this case AC output or DC output in a window range from 0 to 350 volts DC or 0 to 20 volts AC. This allows us to connect different applications like a direct resistance for water pumping, a water pump system, grid connection, any kind of motors, for example, for air ventilation or pumping, or we can use for telecom. Different telecom companies are looking for wind turbines or production that, in this case, can connect directly with their rectifiers. In this case, we can connect through the interface directly to the telecom rectifier, supplying a control voltage between, for example, 100 to 350 volts, and the telecom company or the telecom electronics can control their own battery charge or their own complete system by their rectifiers. Of course, we have the same options that we can connect an anemometer, we have external relays, etc. Okay. In this case, what we develop with this active control of the wind turbine is, for example, placement. We increase the efficiency. We have increased the security of the system per 3. We can monitor, we can remote control, or we introduce the wind plus speed control. In this case, placement allows us to check previous to the installation what happens in this place. If we introduce or if we put a wind speed data logger, we can get the parameters of these placements, and we can do site parameterization. That we can test the wind turbine, we can improve the power curve to this place, or we can make different changes into the wind turbine, like change the blade diameter or make a special power curve to this placement. We will see in examples. We have made an installation in Horn Cape in Chile, that there is a very extreme conditions placement, and we have the requirement to supply a wind turbine that can supply an average of 3.3 kilowatts average in this place. We make a wind speed analysis, and then we take one 5 kilowatt wind turbine with an improved power curve that allow us to supply up to 3.6 kilowatts only, and we change the blade diameter. After more than 5 years, this wind turbine is working without any problem, while before they was using different wind turbines with problems. They installed some wind turbines from our company, and also we have problems. But finally, with this placement or inverse engineering, we make this special wind turbine for this placement, and is working without any problem for more than 5 years at this moment. As I say, we improve the alternator with increasing efficiency up to 96%. And thanks for the active control of the wind turbine, we increase the power production up to 20% in these cases. Triple security, because we have electronic controller, we have torque controller thanks to wind plus speed control, and we have mechanical disorientation by tilting. In this case, I explained before that we was using pitch control into the blades, but was expensive and at maintenance. But in our case, we are using at this moment tilting disorientation, that is only 3 moving parts, and we don't have too much maintenance, only 1 revision per year. Then we have also modularity, so we can change the applications or the use of the wind turbine depending of the needs of the user in this case. We can monitor the wind turbine, we can connect to our platform, and we can see what is happening into our installation. In fact, we are now, we will see in the last part of the presentation, we are now improving more and more this platform, adding maintenance alarms, maintenance information, all the things to complete and to be active between user and us as manufacturer. We have remote control because from our company, from Bornay, we can change power curve parameters. We can update firmware of the controller as many other applications like cars, like inverter chargers or whatever. Or for example, you as user or you as installer, you can protect your installations by turn on, turn off remotely or by switching to safe mode or quiet mode. The main advantage, but we was looking at this in a previous presentation, the first one I think, is the wind plus speed control. In this case, we have an intelligent speed control that works over the power curve or the torque. We make an exhaust analysis of the CP and lambda of the wind turbine. We was looking at the power or the torque that the wind turbine with the blades can produce at each wind speed, at 3 meters per second, at 4 meters per second, at 5 meters per second. You can see in this graphic the analysis of the power curve. And then we design the power curve to control especially each model of our wind turbines. With all these improvements, we have solution for different problems we have into the past. For example, we cannot install a big wind turbine, 6 kilowatts, for example, in a 12 volts battery because the amperage capacity. In this case, we can do whatever, but we have to consider that the limit of that our MPPT charge controller is 125 amps. In this case, for example, we can connect 5 kilowatt wind turbine to a 12 volts battery, but we will get the limitation of 125 amps. So if we connect 12 volts, the maximum capacity will be 1.5 kilowatts. But it doesn't matter if we connect 5 kilowatts. In this case, what we have is better performance at low wind speeds with a limit of production of this wind turbine of 1.5 kilowatts, and the power in excess will be burned in the internal resistance. More problems we have into the past is that, for example, in Latin America or in US, for example, they are not using cell batteries, 12 volts, 2 volts cells that can be up to 2,000 or 3,000 amps. In this case, they was using monoblock batteries, 12 volts, 200 amps, 250 or 300 amps as maximum, many batteries in parallel, and we find that we have a lot of problems with this kind of batteries because the limit of amperage or the limit of amps that can absorb these batteries. We also find that if we connect a lithium battery and we access, for example, voltage or state of charge, etc., we have many problems. In this case, with the Wind Plus, we have solutions to use any kind of battery, small, big, limit capacity, AGM, lithium, whatever we can use. We also find in the past that different installers use fuses to connect the wind turbine to the battery. In fact, there are some standards in different countries that is obligated to put protections between the wind turbine and the battery. And when this protection is disconnected or fuse blow, we have the problem that the wind turbine is free running and do not control. In this case, what we are doing is with our MPPT charge controller, if we disconnect the battery or the battery is not present, as we have total control of the torque of the wind turbine, the control turns off the wind turbine, break the wind turbine until this connection is reestablished. So when we connect again the battery or when we replace the fuse or turn on the protection that was off, the wind turbine will start again. In the past, the problem was that was free running, accelerate, and by fatigue or over speed, we have many problems like broken blades or burning the alternator. This is totally solved at this moment with our solution. For grid connection, we are normally using the interface, and in this case, what we have is wind turbine 220 volts AC output goes to the interface, and interface is supplying to the inverter constant voltage and different amperage. We don't need to program the inverter with the power curve because we have Modbus communication between the interface and the inverter, and we are telling to the inverter that we are producing each capacity at each time. So inverter is adapting the power output to the sentence that we are sending from the interface. If there is a problem, like the grid is not present or whatever, inverter can send a consigna to the interface. There is an error, please turn off, and the wind turbine stops without any problem. We can also make zero injection by using an external compatible meter. It means that if we are using the meter, we can adapt the energy production of the inverter and the wind turbine to the needs that we have in our installation and not inject any energy to the grid. Here is the presentation of the visual monitoring platform, where we can see the power production of the wind turbine in real time, or the production that we have in the last day, month, week, etc. At this moment, we are making more improvements, and we are allowed to check different parameters like voltage, amperage, wind speed, RPMs, braking capacity, temperature, turn on, turn off the wind turbine, different information that we have saved from the wind turbine. And this is what we are introducing the last week, that is maintenance for the wind turbine, where we can have all information where the wind turbine is installed, which components have installed solar modules, wind turbine, batteries, etc. Instruction for maintenance. We have a message box for alerts, for advising to keep in touch user and manufacturer, or to send some information to the users like, your maintenance is not done during the last year, please do the maintenance, or you can have this or this problem. Your wind turbine is showing this and this problem, please do a preventive service to prevent problems. And we are checking the possibility to introduce also in the same monitoring the Victron remote monitoring inside our platform. So with this, you will see your complete system, what is producing the wind turbine, how is your inverter charger working, your solar system, or your consumptions at the same platform. You was talking about the solar and wind turbines, solar and wind production. And in fact, in the last presentation, you mentioned that the solar production is reduced during the last month. In this case, why we recommend to use small wind turbines? This graphical is the energy production of the solar modules, or typical PV production, depending of the month in Spain. If we see, we have a need of energy, especially in the winter months, January, February, March, October, November, December. And we have an excess of production in the medium part of the year, April to September months. Normally, this, if we want to cover 100% our consumption along the year, we need to increase a lot the solar production. And we have a very big excess in these months and a very reduced energy production in the winter months. If we see the typical production of the small wind turbine, we have totally the contrary. In this case, we have an excess of production January to March and October to December, and less production in the summer time from March to September, more or less. If we make the combination, of course, we will get a more stable energy production along the year, summer, winter, independent of the energy consumption we have. And there is also a big problem that normally we are not considering, and can help us to install more wind turbines and to get a more useful and more longer life system. It means if we have a PV system, we have all days a cycle A, E, and B according with the standard. It means that during the day we are charging the battery, but during the night the battery is being discharged. All days, depending of the dimensioning that we make from our system, we are discharging the system between 20 to 60%. And this means a battery life that we can calculate. In this case, for example, we are looking at a standard use of the battery. You can see that each day is discharging between 20-25% more or less, but a day where we have more consumption or the sun was less irradiation, the dip of discharge will increase up to 30, 40, 60%. In this case, we see that this dip of discharge is higher because the solar irradiation was lower during this day. In this case, we have the same installation with the wind turbine or without the wind turbine. Here, we don't have wind turbine, dip of discharge is 20, 30%, but here we have a wind turbine. The days that we don't have wind, the dip of discharge will be 20%, exactly the same, but the days that we have wind, the dip of discharge can be 10%. In fact, if we see the last day of the graph, October 16, in the previous graph, in this one, the dip of discharge goes to 35, 40% more or less. But in this case that we have wind, the same installation, only discharge 5, 10%. It means 20% less discharge of the battery. If we see the comparison of both graphs, we see that we are discharging less the battery. The dip of discharge is less. What happened in this case? We are enlarging the battery life. What happened also, if we are using a flooded battery, normally we need to make an equalization to remove electrolyte and remove acid and water in these cases. If we are using a PV system, this is very difficult because we need to force an equalization. This equalization is normally done by amperage, but if we don't have too much solar modules, this is very difficult, or by voltage, increasing the voltage level, and this is also very difficult if we are using a standard controller. In fact, if we see what manufacturers of controllers tell about the equalization voltage and what is telling the manufacturer of the battery, we see that normally we don't arrive to produce with solar controller this voltage or this capacity to make this movement in the electrolyte of the batteries. For example, the battery manufacturers say for an equalization charge, we need between 15.6 to 17.5 volts DC, and the solar controllers only produce 15. So it's very difficult to generate this equalization. If we see the voltage of the solar modules, for example, 12 volts modules, 36 cells, is charging maximum 18 volts. So depending of the use, it's impossible to make an equalization. In this case, by using a wind turbine, we can increase this voltage up to 70 volts very easy. And the amperage, depending of the capacity of the wind turbine, can be arrived to 120 amps without any problem. So what we are doing by using a small wind turbine is more stable production summer and winter, lower dip of discharge of the battery, that means reduce the cycles day and night. We are doing an automatic equalization battery charge each time that we have a high wind speed, and we are preventing an electrification and stratification of the electrolyte. If we make a comparison between a PV system and a hybrid system, by reducing 20% the dip of discharge of the cycles of the battery, we are reducing approximately 3,000 euros of the cost of the installation. So, or enlarging 30% the life of the battery. So in this case, by using a wind turbine, we should not consider the cost of a wind turbine. We should consider also the safe money that we are going to have along the life of the system, along the life of the battery, for example. Concerning applications, off-grid, battery charge, very easy, wind turbine by hybridization with solar modules, both using different controllers and charging a battery bank, and then the inverter charger to supply to 20. Direct water pumping, we are using the wind turbine with the interface connected directly to the pump. In this case, we are using DC pumps like Grundfos EQ Flex or any 220 or 380 volts AC single or three phases water pump. Grid connection, we are using the wind turbine, the interface, and a grid connection inverter. Normally, we recommend, in our case, SMA, Sunny Boy, or Sunny Tree Power, because we have more implemented the constant voltage or the communication between the grid connection inverter and the wind turbine. But we can use any kind of grid connection inverter. Telecom, by using a standard application or by using the interface and using the rectifiers of the manufacturer of the telecom system. At this system, we have, at this moment, we have more than 12,000 installations around the world in 63 countries. And these are some examples of the wind turbines. This is 1.5 kilowatts in Cayo y Codina in Cuba. This is in Tanzania, 2 wind turbines, 5 kilowatt system for rural electrification. We have microgrid systems in Venezuela. We install around 60 systems in these communities. In Canada, a wind turbine, 25.23 kilowatts for off-grid application. These are the Spanish Antarctic expeditions. We are present in both. We have 2, Juan Carlos I and Gabriel de Castilla. In both bases, we have wind turbines. In Gabriel de Castilla, we have 1 5 kilowatt wind turbine, and Juan Carlos I, we have 2 wind turbines, 3 kilowatts. This is an Spanish installation for telecom using 3 kilowatt wind turbine. This is the installation I mentioned before for the Chile Army in Horn Cape, with a 5 kilowatt wind turbine with reverse engineering, and this wind turbine is 3.6 kilowatt maximum and a different blade diameter. This is in Green Cape, 6 kilowatt wind turbine for off-grid domestic application. This is for telecom. This is a trailer that can be moved for different placement for telecom uses, and you connect the wind turbine and the solar modules to the trailer and you have the service. This is in Mexico, a grid connection system connected to the CFE, yes?
Yeah, if you could move towards the end, because we are running a little late with the presentation.
Yes, there are only 2 more pictures and it's enough. Thank
Sorry
you.
about that.
Sorry. This is in Iceland, wind 13, 1 kilowatt for telecom users. You can see our team. The last meeting we do in this summer. We have collaborated with different organisms for different projects in the university, and these are the different institutions where we are in cooperation. You have here our contact information, and of course, if you have any question, I see in the chat a couple of questions, I think, that I can answer.
We can take the question from Adrien, and then the others can just write in the chat directly to him, and then we can go ahead with the program afterwards.
Okay,
so Adrien, what was your question?
To the chat. Thanks a lot for your invitation.
Thanks a lot for your presentation. Adrien, your question?
Yeah, I had a question about the MPPT controller. Is it a passive diode rectifier with then a DC-DC, or is it an asynchronous rectifier?
I am not sure because I am not technician in this, but I think it's if you want, I can check and I can give you an answer by email if you want, but I am not sure. I need to check with our technical department.
Okay, thank you.
Okay, thank you very much. So we remain to Spain now. We have Ignacio Cruz from CIEMAT, who is going to present now. And he's head of the wind energy unit with a background in electrical engineering and more than 30 years experience in the field. And now he's also part of the EIA Task 41. And his presentation will focus on potential solutions for lowering the costs of small wind turbine. Ignacio, are you on? Yes, you can see. We can see your screen. Perfect.
Okay. Good morning to everybody. Thank you, Danielle, and thank you, Tommy, and thank you to all the staff of Folkecenter for inviting me to this interesting workshop. So I'm going to present here an overview about the work that was done in the frame of the Task 41, the International Energy Agency. And the main objective of this work was just to find solutions, so potential solutions to reduce the cost of levelized cost of energy on distributed wind. And one of the idea was just to find potential downscaling ideas from medium or large wind turbines to small wind turbines, in order to refine the design of the small wind turbines. So this was the main aim. We had identified several potential ideas, and the second phase of the activity was just to analyze the cost benefits of the different ideas identified. And this is still ongoing, this work. So this is a progress view of this activity. Let me see if I can. Oh. Okay, this is the. So this is the scope of the work. I want to mention that this work has been done by several partners of Task 41, so mainly for Ian Baring-Gould and Trudy Forsyth from NREL and from Wind Advisors, and some other partners from this task were working on this activity also. So the first question is just to define the design changes that using large wind turbines that could be downscaled for distributed wind turbines in order to reduce the distributed wind LCOE, levelized cost of energy. Some of the ideas that we are going to see here has been already mentioned. It's really interesting that it has been mentioned in other presentations today, previous presentations. But this is really interesting just for us to see that these ideas can go forward in this aim to reduce the cost of the energy produced by the small wind and to be more competitive in the future. So another question is how to resolve technical issues with the smaller wind turbines below 30 kilowatts and less, maybe where downscale is not necessary. So those are the research topics, the ideas. So some of them are very, very well known, as just to design wind turbines with taller towers, wind turbines with lower specific power. So it's important that if we analyze the potential of reduction of cost of wind turbines, so there are several areas of development, like for instance, learning by deployment. So it's strongly dependent on the market, how many wind turbines are going to be in the market. So learning by research, this is more or less the activity we are addressing here. It's very important just the supply chain dynamics, how the supply chain is operating. So for instance, it has been mentioned the collaboration with other companies from the automobile sector like Toyota. So this is very interesting in order to produce potential reductions. And obviously market dynamics. So this is probably the more difficult even in this situation of high cost of energy. So this is one of the most important, the key points in this activity. So lower specific power turbines is very interesting. So in large wind turbine, this is going in order to extend the application of the wind turbines to areas with lower wind resources. And this is very related to the deployment, the high deployment of the big market needed or expected. So behind the meter grid services, so this is interesting. So the big market is working on that just to get benefits from the support of the grid system. Why not the small systems? Don't mind if it is just a standalone wind turbine or a hybrid wind solar system can support also all the requirements of the grid codes. Grid codes are getting more strict nowadays, so all requirements should be a very interesting opportunity to get benefits. Life cycle cost of isolated power systems has been already mentioned. So these isolated power solutions are really this is the real niche market of small wind. Value of the integrated storage. This is very related to the cost of the storage solutions and the regulation. So it's very related to this, but it's clear that it's going to be all these systems are going to be face-to-face with a storage solution, but the cost of the storage solution is one of the main inputs. And value of optimization and distributed generation within the region is important in order to get a sufficient critical mass just to develop the distributed wind. Just in order to be, obviously, we are not talking about wind farms, but we are talking about several installations that are nearby, not very far each other. So in order to establish a critical mass mainly for operation, maintenance of these solutions, to reduce this cost in the operation in the future. Reduced weight wind turbines. This is very related to the materials, to the new materials, to the new design solutions. We can learn something from large wind turbines that are modular solutions. This is another important issue. Direct variable frequency applications. So production of ice, water pumping, irrigation, water desalination, direct heat, even hydrogen. Direct hydrogen production. Nowadays, maybe very costly or but this kind of solutions, distributed wind can support and offer interesting solutions. Some of them more costly or some others more general. Some of them has been already mentioned as here as in this conference as a water pumping or irrigation, but others like hydrogen are still ongoing or just looking for the competitiveness. So, optimization of installation methods and foundation design. This is an important thing. So, foundation is competitive solutions for installation, avoiding cranes, costly cranes, or foundation designs, standards for different soil conditions for different that can make easy or reduce the cost of the installation of the wind turbine are really strongly recommended. Some activities related to this have been already done for small wind turbines manufacturers all over the world. But I think that maybe standardization in order to reduce the cost, standardization, and systematic approaches to reduce maintenance for the distributed wind fleet. So this is very related to the distributed generation within a region. And there is a horizontal area which is showing large wind now. There is a great interest on industrialization. So cost reduction by the industrialization of the different components. So no using 3D printing solutions, so standardization and industrialization. So I think that this is a pending question in the small wind. So related to the supply chain industrialization, so in order to reduce, it's clear that it is a big market is required just to deploy these strategies. But it's this is a question that is needed just to be solved or to be developed in the future. So, but all these research topics, all of them need cost model for LCOE comparison in order to see what strategies are good or maybe not for the future. So if we look at the research topics, taller towers, so for largest wind turbines, the economies of scale allow for the consideration of taller towers. But for a smaller distributed wind technology, the cost of towers is typically half of the turbine system cost. So the sensitivity is really important. There are some questions about this topic, like what are the trade-offs between towers and large and distributed wind turbines? What are the logistic impacts or drivers, such as crane heights, shipping, or transportation of tower? Can different materials for towers and foundations impact some of these decisions? Is there an optimal height for different sites based on wind shear patterns and site characteristics? How can handle permitting and social acceptance issues with increased tower height? It's a really important issue in distributed wind. Is there a need? It's very close to inhabited areas. Is there a need to analyze the uses of different tower types and heights for specific wind turbines? So those are questions that can be resolved in the development of the work. So, for instance, if we look at the taller towers for large wind turbines, we see here what is the expected reduction in the levelized cost of energy versus half height wind turbines, and we see that we can get even around 7% of reduction of the LCOE. But we need to take into account the cost of the solution, the type of tower that we are going to use. So anyway, this analysis is very related to the very precise wind resource assessment in order to know what is the wind shear, what is in the site where we are going to install our wind turbine, and cost competitive tower is interesting also. Which solution is the best? So we have seen tubular towers, or we have seen different solutions. So especially for downwind wind turbines. So which is the best solution? Even if we need to install a tall tower to get a better LCOE in our system. Lower specific power wind turbines. So it's clear that larger rotors capture more energy, and there in the big wind sector, so it has been developed so many lower specific power wind turbines, and especially for sites with a moderate wind, which is the most standard situation all over the world. So this is really interesting. The important thing is what is the increase of the cost, the capex of the wind turbine, because of the larger wind turbine or even the larger control system. So this is really important. So we need to analyze the situation, and we need to develop solutions, different solutions, in just according to the standard, the IC standard. So in the end, there are several classes of wind turbines. So in large wind turbines, this is very common, but in small, medium-sized wind turbines, medium size is getting better, but it's really strange, or very rarely we can see different wind turbines with the same power and different swept area of the rotor. But this is interesting just to adapt to the wind turbine to the site conditions. But obviously we need to know perfectly the wind resources system before to choose the best wind turbine for this place. This is, in my opinion, one of the main problems or issues about barrier. Because small wind turbines are installed in unknown locations, so obviously developers or OEMs are tend to develop, to design heavy machines with high factor of safety. So there is this in one way is just about opportunity to reduce the cost if we develop a better solutions. For instance, just to embedding solutions, just to analyze the health of life of the wind turbine. Better solutions just to assess the site resource. Better solutions, so something like twin solutions just to know the situation of the wind turbine. So we can adapt some of the methods that are already used in the large wind sector to the small wind sector. We have also some questions like what are the standard rotor, generator, and power converter cost, loads, and reliability trade-offs to lower specific power wind turbines? Are there appropriate methods of assessing the wind resource at distributed wind customer locations that can encourage the use of low specific power wind turbines? It's an interesting question. In general, is there an optimum specific power wind turbine for the distributed wind market? What are the component changes needed to lower specific power? How will changes to the component impact the full wind turbine design? What are the likely near-term component innovations? For instance, we are talking about extended blades, for instance, or modular power electronics in order to adapt the easily cost-effective solution, the wind turbine for the site wind resource available. So there are some comments about the possibilities of, here we can see some comments about the possibilities of lower specific power wind turbines. For instance, it's clear that lower specific power wind turbines reduce the LCOE, but for instance, innovation in blade design and materials is required. So in order to minimize the scaling-related cost increases associated with larger rotors. So this is an important thing. So research is needed just to reduce the cost of this larger blade. Another comment is the overall analysis suggests that under reasonable scenarios, low specific wind turbines can play a significant role in the future. LCP turbines will provide a higher capacity of utilization factor, even in low wind sites, and may reduce the levelized cost of energy to an extent of 60%. So this is just an analysis for large wind turbines. So the idea is just to develop this, to analyze the different components for the small wind turbines. is more difficult because of the lack of information, available information, but this is the idea just to develop in the future in this work. So the main achievements or main requirements are always the same: the precise wind resource assessment and cost competitive blade design and material as a first component in this strategy, but also something about the power electronics is required of the system of torque control. Obviously is needed. Modularity could be the solution. Another third research topic is behind the meter grid services. So this is a very interesting because we can value these energy services with even with small wind turbines, especially for grid ties applications. There are some questions, obviously, what is the economic and technical value behind the meter grid services for industrial plants in different countries with different power costs? It's strongly dependent on the regulation. What is the economic and technical value of distributed wind in front of the meter? Are there optimal locations for distributed wind at present? Are social acceptance issues that need to be addressed? What are the different costing models for compliance with different country laws? So resource assessment is always needed, site resource assessment, but also in this case, the regulation, the country regulation, grid code of different countries is extremely, this strategy is extremely sensitive to this, to the regulation, the local regulation of the grid code. Life cycle cost of isolated power systems. So,
Ignacio, sorry, about 5 minutes left.
Thank you, Danielle. So this is another important, so our markets are more likely to use PV than distributed wind. It has been already mentioned because of the cost of different cost of the systems. But there are also an interest to analyze, to develop models and tools just to develop these strategies of isolated solutions, hybrid solutions, which are really interesting. And in terms of LCOE, total LCOE of the whole system. Value of the integrated storage. So storage is interesting, and also to offer the energy produced by the distributed wind system in the best period of time, in the high cost period of time, but cost of the solution and the integration. So the solution required just to integrate in a optimal way the electronic solution. So it's needed to be addressed, and general cost of energy storage, adequate sizing of energy storage device is really important just to integrate in the right way in the system. Value of optimization of the distributed generation within a region. This is very important in order to get a critical mass, it has been already mentioned, especially related to the operation and maintenance of this kind of solution. So in order to reduce the cost of these activities. Reduced weight wind turbines. So this is clear. Some wind turbines are really too heavy, just in order to develop a very robust solutions for every site. So the idea is just to define different solutions for different conditions of wind resource. So this is really interesting, but it's required a very good wind resource assessment solution. And it's very related also to logistics, all related to installation, cranes, and so on. It's all related to weight is very important. And also materials. What materials, new materials are offering solutions, low weight solutions for wind turbines. Very variable frequency applications. It has been already mentioned, wind turbines just for specific productions, like ice making, water pumping, irrigation, direct heat, even hydrogen is a good solution. The system in the end it can be simplified. So this can affect to the cost of the energy produced and the final cost of the system. So, but also precise wind resource assessment is important, and competitive power electronics, because it's very dependent on the technology, power electronics, power conditioning. So finally, we address the installation methods and foundation design. Yes, in order standardization is really important in these topics for different in order to have several solutions for different types of soils or different in order to reduce the cost of the installation and the foundation. So some developments has been already done, but I think that the standardization is still pending. And strategies to reduce the maintenance of distributed wind fleet. So this is really very related to regional to the way to develop the distributed wind in order to generate enough critical mass. Development of multiple installations in nearby sites is really interesting in order to establish a cluster, something like a wind farm, but in different areas, in different sites. Should be interesting in order to reduce the cost of the system. And that's it from my side. So if you have any question, I will be happy to answer. Thank you.
Thank you, Ignacio. Is there any short question? Yeah. No. If there is any question, I cannot see it on the screen.
Okay.
Otherwise, yeah, thank you a lot. And we move now to a little different branch of wind, which is airborne wind. We had a presentation in a couple of editions ago of a specific company, and this time we have the organization which tries to combine all the companies working with airborne wind. So I would like to welcome Kristian Petrick, who is the Secretary General of Airborne Wind Europe, and he has a lot of experience in policies and strategic advices both for public and private sector. And on top of that, he is also involved as Airborne Europe in the IEA Task 48. Kristian, are you there? Yeah, I can see you sharing the slides already.
Can you hear me?
Yes, perfect. Welcome.
Okay, great. Yeah, thank you very much for the introduction, and thank you very much for inviting us to this conference. Indeed, we are somehow different, but we are also considered small or medium at this stage, and I will explain a little bit further what airborne wind energy means and where we are currently. This is just an overview of the association. We have about 20 members, of which some 12 are developing the different airborne wind energy systems. We are a member of Wind Europe. You already mentioned that we have our own task within the IEA Wind TCP. And then you see here that we are also members of a number of other networks, among others, the Alliance for Rural Electrification, because our systems will actually have one of the main entry markets in the off-grid and distributed energy markets. And I will also explain that in a moment a little bit further. So I will give you a short overview about the principle and concepts, the advantages, markets, and the current state of the industry, and then briefly discuss demonstration commercial site that we are looking for. And I'm happy that Ignacio was presenting just before me, because we also actually visited CIEMAT almost a year ago, the site in Soria, to see if that would be a site where potentially airborne wind energy systems could fly. So let's see if that will become a reality in the near future. So our technology consists basically of two main types, where we see that there's some convergence. There will be soft wing systems that are like big kite surfing kites that you see on the upper side upper row, and then fixed wing systems that are more like drones or small airplanes. And the principal power generation concept is the so-called ground generation or yo-yo principle, where the kite flies out in figures of 8 and pulls a tether which is wound around a winch, and then next to the winch you have the generator on the ground, which produces the electricity. At one point the tether is reeled out, so the kite has to fly in again to the starting altitude, and you need a little bit of energy and time to reel in, but it's much less, so it's about 15 to 20% of the total power that is being produced during the reel out phase. So, but yeah, you have this yo-yo principle or pumping kite system, which can be applied for both soft wing and rigid wing systems. Then the other type of generating is the so-called fly gen, where you have the power generation on board. That means that you fly like a drone, vertical takeoff, you fly into the wind, and then you start the figure of 8s, and you turn the propellers and the motors basically into generator mode, so you produce the electricity in the aircraft and evacuate the electricity through the tether to the ground station. There are currently 2 companies that are pursuing that concept, and we will see which one under the fixed wing systems will actually be the one that will be further deployed in future. But both are very promising. Now I will show a short video, and I hope you will see it there as well, of the most advanced system, the SkySails power system, about 150 kilowatt in Mauritius. So that's the first commercial system, basically. You see the automatic launch from a mast, 15 or 18 meter long mast, from which the kite is being launched. It's going with the wind up into the air and then starts the power cycle in figures of 8. So you see that this is a containerized solution. You basically have a very small ground station. You even don't need to put any foundation because the ground station is heavy enough to withhold the kite. So there's there's nothing required except that it's a rather flat area. Here they put some concrete apparently, but it's not so much. And then, in case there's no wind or you get a hurricane or anything like that, then you would pull down the kite and land it again. And that also can be done automatically so that there's no people involved. Not all companies are there yet for full automation, but the majority also for the fixed wing systems can do that already. And all of them will have or will be full autonomous in future. So what are the advantages of airborne wind energy? The first advantage is that we get into higher winds at higher altitudes. Here you see the wind map of Europe at 100 meter fixed height, so basically the normal height of the nacelle. And you see that the best wind above 7.5 meters per second in the reddish colors is basically all offshore. But we all know that there is also wind turbines onshore. But now if you go or can go up to 500 meters, then you see that you get basically offshore conditions also onshore. And this is a major advantage of these kind of systems, because as you know, the power output increases to the cubic factor when you increase the wind speed. The other big advantage is that we need up to 90% less material, because we only emulate basically the wingtips of a conventional wind turbine, and we get rid of the tower, most parts of the foundation, and the blades. And that's the other big advantage, because that gives us potentially lower costs in future and many advantages also in the supply chain. So under the circular economy approach, we basically reduce from the get-go a lot of the materials, and now wind energy we know is already quite good, but we can even be better by reducing further. That will help us, these mass scalings that you see that are required in the future here from a JRC report, on the technology-specific materials. So these are also rare earth materials, and then but also structural materials like concrete and steel. They will all be a factor 10, 15, even up to 40 required to build up all the capacity that we will require for onshore wind or on and offshore wind. So if we can help to reduce a little bit this material amount, then that will be definitely advantageous. And first studies also show that since we have in most of the systems the generator on the ground, we are not, we can use heavier materials or don't need rare earth materials for the generator, which has other additional advantages. Then a recent study even showed that onshore airborne wind energy significantly outperforms onshore wind turbines just because of this higher capacity factor. We have to see how to deal with that in future because we are not there yet, and we need the same amount of capacity per square kilometer where the systems are not at this size yet. But you see that in future there will be this decision may have to be taken for certain sites if it's more advantageous to put an airborne wind energy system or a horizontal axis wind turbine. So markets are basically all the markets that normal wind could go as well. But since we are logistically easier to handle, especially off-grid and remote areas, or mines are definitely markets where it will be of interest. But then also floating offshore, because also here the material advantage and the reduced logistics will help to get into deeper seas, because we basically just need a landing platform and just smaller platform basically without the large towers out there in the sea. But this is still for the future. At the beginning, all companies are focusing on onshore. So yeah, that's another way of showing it. Basically, this replacement of diesel generators in remote areas is one of the key markets at the moment. As long as we don't have specific support schemes for grid-connected systems in Europe. So that's definitely something that we are trying to achieve, that the different member states of the European Union or other countries give us either feed-in tariffs or CFDs or whatever is required, or what PV and wind also received in the beginning of their until recently, or still in many countries. And we need that specifically for airborne wind in order to be able to enter into the market and to upscale. At the moment, we are about 20 cents per kilowatt hour. So that's also the feed-in tariff that we kind of ask for at the moment. And we will see if some countries, we are especially active in Germany on that, will go ahead with that, and hopefully we'll get this to connect more systems to the system. But yeah, you see that 20 cents, or you know that 20 cents per kilowatt hour is already lower than diesel-based power generation. So in remote areas, we would be, or we are already competitive. So where do we stand right now? Just an outlook, or basically a status how we are seen. Most, or basically all major studies that consider airborne wind energy from the European Commission, from IRENA, NREL, UNFCCC, all say that this is a promising technology which should be further explored. So it's not that there's not any report out there on an official one that says this is a dead end, but actually all of them see potential, but they all also say, well, more needs to be done. So we need further R&D support, but also a market price support, as I mentioned before. The advantage for Europe is here that most of the organizations that work on airborne wind, so both in terms of technology development, but as well as research, are in Europe. So we have basically an advantage here, but there are also a number of institutions in the US and also Japan and other areas. We are not really sure what's happening in China. But yeah, basically in Europe, we should try to keep this advantage, hopefully, and build up a new sector for airborne wind energy in Europe to have a competitive new technology here. There was very briefly you have seen already the IEA task. So we are the Task 48, started about 2 years ago with these 5 work packages. We have 11 countries that support us, and any other countries here in the call or institutions who are interested are willing or are very welcome to join. See resource potential markets, reference models, tools, metrics. Some of these points that Ignacio mentioned are also part of that. Safety and regulation is definitely very important because we are flying up to 6, potentially close to 800 meters. So we go into the airspace and have to share that airspace with other airspace users. So we have to deal with that, and we have make some proposals on how to organize that. If there are questions on that, I'm happy to reply to that later. Social acceptance is very important for us. We don't want to run into the risk that that there are a lot of people that say, well, we don't want to see that. So we want to avoid what is partially happening with the wind sector, that people just don't want to have us. So we want to be very open and transparent from the very beginning and hope to get support there also from local population involving energy communities and so on. And we are working on several life cycle analyses within Task 48, which will, a few are already published and some more are to be expected in the next months. Last year, we published a white paper commissioned by us, but written by an independent consultancy, BVG Associates, about the future of airborne wind and the roadmap, so to speak. You see here that we could, if we have the same upscaling curve as conventional wind had from 85 to 2010, starting in 25 for us, we would reach several hundred gigawatts in 2050. We think we can also already, well, the last year, basically, we think we can even be more bullish on this one. But yeah, we have to get on this curve, and therefore it's important really to get political support. And then for the cost, the same, we can run down pretty quickly, we think, on the cost curve if we have the right support schemes in place. There are some opportunities currently with the Renewable Energy Directive. I still have not exchanged this here, so it's now defined. It's not only will likely define, but it's there now in the new revised directive. There's a 5% target for innovative renewable technologies, and we think we are, or we can help achieving that target because we are definitely one of these innovative technologies. So we also hope to get into the NECPs, which are due in their final version middle of next year. Then there's this European regulation for unmanned aircraft systems, which also helps at least the fixed wing systems to be quicker deployed in different parts of Europe, because if you have a permit in one country, then you can do a transporter permitting procedure and then rather easily go into another country if you operate under similar conditions. And then this current focus on faster permitting will hopefully help us as well. Because acceleration of another renewable electricity deployment is something that is urgently needed. Then briefly on the demonstration and also actually commercial sites. So we are looking for sites in Europe in order to reduce also the logistics. Well, basically the small teams that are working on these systems have to travel too long. So we are looking for these sites in Europe at the moment. Just 2 days ago, the site in Ireland was inaugurated under this MEGA-OR project, this Interreg project that you see here in the top logo. And there will be hopefully more to come over the next years. And these sites will help us to optimize the systems and then really deploy globally with a lot of potential for export and in all these different fields that we think are potential markets for us. Just to get an idea, what we are looking for is basically rather flat areas. Well, they can be also hilly as long as there are no major peaks or no high structures in there. About 800 to 1,000 meter radius around the ground station. But there are also systems that are flying with shorter tethers, so it can also be potentially less. But yeah, we need something where you don't have roads or other buildings or so on, just in case the kite comes down. So that's, yeah, we're getting safer and safer, but you never know. So it's important that we don't fly across any roads or anything. But yeah, agriculture and things like that can still happen underneath. If you have a bigger site, then you could also, then you wouldn't place the systems with, I don't know, 2 kilometers distance, but you can pack them closer to each other because you can steer the kites in a way that they are flying in a synchronized way, or, well, at least in a way that they don't entangle the tethers. So that will be all possible. We have just done recently a study for Germany on the airborne wind energy potential. And under these different conditions that I just mentioned, we get a potential of between 12 gigawatts and even up to 100 gigawatts with shorter tether length. So we have to see where we end up, but it's not that even in a country which is very densely populated like Germany, that there wouldn't be sites available. That's actually, there are quite some sites where these requirements are being met and we could be deployed. So to end this presentation, 3 main points to take away. So we may be the single most important new renewable energy technology because we tap into this high altitude wind that where no other technology can tap into. So we think that this is really a major opportunity for Europe to be setting up a new industry in that field. We are a reality, so we have the first commercial systems available. We have basically all the systems have shown that it works, and there are no technical or other major showstoppers anymore. So everything what is now required for deployment can be solved, as it could be solved for other renewables as well. And we require political support because that can speed up the airborne wind energy potential. So this public funding will be required for research, but also for remuneration of the power produced. Again, we also think that there's no major risk for policymakers because if we don't produce so much, then we also don't receive so much money. But there needs to be political support, and that's why we say ideally we would develop a European airborne wind energy strategy together with the government's agency, the European Commission, and us as a sector. To see how this technology can really make a major impact. And with that, I will finish my presentation. You see here real projects in the different countries and islands. And if you have any questions, please let me know. I'm not sure if you still have a few minutes because we are run over time already, but I am available.
Thank you, Kristian. So if there is any question, please come in. Yes, we have a question here from the audience.
Yes, I have a question about the maintenance cost of the system, because we have a not durable system in, let's say, the wire, the rope, and the kite, and you can't maintain these things. You have to exchange them. So the first question is, how long will they last for the exchange, and how high are the costs in the maintenance for the overall lifetime? Thank you.
Yeah. So indeed, especially the soft kites don't last forever, and the tether neither. So SkySails, for example, they think that kite may last some, depending on the conditions, depending on the wind conditions, maybe 9 months to a year or so, and then it would have to be exchanged. And the tether the same. so up to a year maybe. Potentially, at the moment they think they would exchange the entire tether, but further going on and optimizing, maybe only the lower part needs to be exchanged, because that's the part that constantly runs around the drum, and the upper part is basically not being used so much. So indeed, these costs need to be factored in the LCAs. They are factored in, and then they are also factored in the LCOE calculations, and they are potentially higher, at least in the beginning, compared to conventional wind turbines, because we need more operating hours and see if it really works. And you need, especially in the beginning, also due to permitting, you need people on site who can bring down the kite in case there's something happening. They don't let you fly without having someone supervising it, but all these are things that in the future will hopefully disappear, so then these operating costs will go down. But yeah, they may be potentially higher than for conventional wind turbines. Just mention that this exchanging of the kite is not necessarily a disadvantage, because in the meantime, better kites are being developed, so you can always exchange the old kite with basically the last generation of the new kite. So you could even upgrade systems slowly over time, leaving the ground station at the same capacity, or making the ground station basically set of that can only deal with 150 kilowatt. You may already put one that can deal with 250 or 300 kilowatt, and then you increase the power of the kite over time and the performance. So that's actually an advantage of this cycle. And the fixed wing systems, we will have to see how long they last. Maybe not 20 years, but they are supposed to last quite a lot longer than a year.
Thank you. Any other question? Nothing from the chat, right? No. Okay, so thank you, Kristian. Should there be any more questions, then they can just write to you, of course. Now we would like to welcome
thank you.
Ulrich how? Yeah. Sorry. Close enough. Who is managing director of Viking Wind Power, and he has a lot of experience in the field, both as big wind and small wind, from what I can see from right here. So you have the clicker.
Yep. Okay. Yeah, I'm gonna show you a little bit about our company, but first I would like, coming back to Ignacio's presentation, that is more or less how we developed the Viking turbine, taking not a big turbine, it was a 250 kilowatt turbine from Hakan, and then we resized it to our, that's fine. Yeah, it's moving. Yeah, so what Ignacio shows actually how this turbine is developed, but I'll just run you through this presentation. As Danielle told me, I have been in the business for almost 30 years, 18 years in the big wind industry, working with transport, installation, service, quality management, lean, in a lot of different companies, in Jamaica, Investors, Siemens, and Suslon. For the past 10 years, I have been in the small wind as managing director of Viking Wind, former HS Wind, and also I'm at the advisory board of the Danish Energy Agency representing small wind. The company profile is we are doing a wind turbine up to 25 kilowatts. At the time it was developed, the maximum size in Denmark was 25 kilowatt, tip height 25 meters. So we developed a 25 kilowatt turbine at 24.5 meters. We were established in 2009, we're located in Randers here in Denmark. We have 4 full-time employees and 2 part-time employees. Up to now, we have installed 74 wind turbines worldwide. The company was founded by Henrik and Sven. That's why the HS came from. And they were doing prototyping over a couple of years until they got their first type certificate in 2011. In 2013, a group of investors came into the company and they wanted to hire a new managing director. That was me at that point in time. So I have a 10 years anniversary in a couple of days, actually. In 2014, the group was reduced to from 6 investors to 2, and that is me and a farmer from the southern part of Jutland who invests in a lot of small companies and see them grow. And yeah, he has been supporting us for the past 10 years. We're very grateful for that. In 2017, we rebranded HS Wind to Viking Wind for more friendly and easier to go into export markets. As when you have to say HS Wind, that's pretty difficult, and I don't know how they will pronounce it in French even. So, all of our employees have more or less a history like me from different companies, from big wind, and almost also 30 years of experience. We call it powerful simplicity, but also powerful technology. The Viking Wind was developed as a normal turbine, and now we have introduced inverters to optimize the power output, but also for the grid connection regulations here in Europe. We use a 2 inverter controller system, one to run the generator or the rotor with variable speed, and one to connect to the grid. So we always can connect to more or less any grid. We can also adjust the output. There are some different regulations around the world. Before we had a 10 kilowatt limit here in Denmark and a 25 kilowatt limit, so that was one of the advantages with this one. But also in Japan we have a 20 kilowatt. I think in Belgium it's 15, so we can adjust to that with the same turbine. We just change some parameters in the setup. This is how the customer sees the monitoring system. There are no direct display on the controller, but there's a web page where you can see different parameters, wind speed, kilowatt, temperatures on main components. The monitor system goes through our server where we store all the data, and it will update every 30 seconds for the viewer on this screen. This is how we see it in our surveillance system. So we have a screen where we can monitor all the turbines and see if there's an error of some kind. And we have more specific details on our screen, so we can see how the grid is performing, frequency, etc., etc. So it's pretty easy for us to see what is the error and what can we do about it remotely also. So we can, I think, 75% of all errors we can adjust remotely. The Viking wind turbine is also easy to install and to perform maintenance on. It is designed for easy transport and installation. Here comes the elevator speech, as we call it. We can transport 3 complete turbines in a 40-foot container. The heaviest lift is 1 ton, and the turbine is erected by an electrical winch that we bring and mount on the foundation. Maintenance is more or less the same. We lower the turbines so all work can be done on ground. The first maintenance is done 3 to 6 months after erection, where we go through all the bolt connection, safety system, etc. And after the first maintenance, we have a yearly maintenance. To keep track on all the things we have in the turbine, we have made a database. So when we build the turbine, we enter all the serial number on main components, so we can see if we get an error. If there's a serial error or something like that, we know exactly where to find it and in what turbine it is. Also for maintenance, we keep track on when was the last maintenance, when is the next maintenance for planning. Also we have a logbook where we can see what has been done at the maintenance, or what if we go on a call out, as we call it. Between maintenance, we can also see what has been done. Also, this is in a physical logbook in the turbine. That's a requirement these days. But the same we have in our database. And of course, we make a service report every time we have done the maintenance, and also we enter it into, here in Denmark, to a system for keep track for the Danish Energy Department. Our availability on the turbines is actually quite good. As we think the latest one was around above 99, and including our prototypes and test turbines, we are above 98 in all of the Danish turbines, at least. We run different projects around the world. This was a wind diesel project in Argentina, actually erected 10 years ago, just before I came into the company, and I was closing the project down. And it was a village out in nowhere in Argentina with 500 citizens or so. They had an old diesel generator. Then they got a new diesel generator and 3 turbines, and they actually saved something like 40,000 liters of diesel every year. We have participated in a hybrid project here in Denmark on the island Vejrø. They had only diesel generated and district heating from that diesel engine. Now they run wind, solar and battery storage, including diesel also for when they cannot produce enough. But it has been a very successful project and very learning for us to combine wind with photovoltaic and battery, and diesel for that matter. We knew the diesel in all ahead, but combining all 4 parts is a bit of a task. We're also testing for cold climate in Greenland. It was installed in CIEMAT in 2018. And we had some difficulties with the foundation. It was meant to be directly into the mountainside with anchoring. And I think in the future we will do that, so we will actually use the mountainside because we have this wire system. We can do that, and it's something we look forward to when we go into all the different sites in Greenland, hopefully. We have no special equipment besides the supplied winch to erect it until the turbine, and we were looking at a site in a different place where we actually also could use the winch to drag the components uphill to a site and using the mountainside as anchor. So I think it's a promising project we are doing here. The experience from cold climate is that, well, it wasn't that windy side, but nevertheless we gained a lot of experience, and we changed, for instance, gear oil to a thinner oil, and we had a stronger yaw gear. There were some issues with condense in the controller panel, but we fixed that with the heating, and now we have a complete new controller cabinet that takes care of all of this. Also, if we go into the higher temperature, we can add cooling to it, as we do with heating in cold climate. But all in all, I think it was minor issues putting the turbine up in Greenland. Next step is Japan. I have made a small movie here. I could try to see. I think it will start by itself.
Yeah, I just need to optimize for video.
Yeah, I don't think we need the sound because it's just music. But nevertheless, we are working on a Class NK certification for Japan, where we see big potential for our turbine. And our agent over there is just waiting to sign contracts. And as soon as we get these Class NK certificate, we will be in safe haven, and it will increase our production number by a lot. We are looking at 100 turbines a year, so for the next 3 to 5 years. So if it won't start, I can...
Yeah, we can put the link afterwards.
Yeah, it should be linked so people can see. There's also a movie from Argentina, but it takes 10 minutes, so but it's in the link. So, yeah, for more information, don't hesitate to contact us or check our webpage. You can contact me or Pia Jacobsen, the head of sales.
We have a question from Ignacio.
Yeah.
Thanks for the presentation, of course.
Ignacio?
You need to unmute yourself.
Hi.
I have a question. So you mentioned that the wind turbine is installed in CC in Greenland. So the site was
moderate wind site. So far I know this wind turbine has there are 3 different models, 10, 20 and 25 kilowatts. And all the 10 are developed with the same rotor diameter.
Yes.
Which is the wind turbine that has been used in this moderate winds? It's 25 which the wind turbine is. So have you installed a?
It's a 30 kilowatt generator, and it's 30 kilowatt inverters. So it's the same components, hardware components we use. So it's only a matter of changing parameters in the controller about the output. If that answers your question.
Okay, thank you. It's okay.
We can actually produce 1 kilowatt at a medium wind side for around 15 euro cents per kilowatt. So that's why we're also competitive with diesel generated power.
Really competitive, yeah.
Being so easy to transport and install, we can go almost anywhere.
Thank you.
Very good.
Are there
Thank
any
you.
more questions? Doesn't seem so. So thank you very much, Ulrich. So now we will have our big break. So for those of you who are in the part of the world where it's night, it's a chance to get some sleep as well. We will be back at 2 p.m. Danish time, so that's about an hour and a half from now. Thank you everyone, and see you later.
Nå slukker man.
Welcome back. Now this second part of the session will be mostly towards the speakers will be mostly from the other side of the water, where now it starts to be morning. So to begin with, I would like to welcome Lindsay, I'm not sure if it's pronounced correctly, who is an earth scientist and has a lot of experience in offshore and distributed wind. And she is also developing wind resources assessments for communities. Lindsay, are you in? Hello, nice to meet you. Perfect.
Thank you so much, everyone, for joining us today. And I'm going to discuss the newly released Distributed Wind Market Report 2023 edition. This report shares information about the small, medium, and large wind industry in the United States, where the energy that is produced is dedicated to serving a nearby load instead of being sent long distances away. In order to create the Distributed Wind Market Report, we need to gather data, and we gather a lot of it. This year, we issued 480 data requests to manufacturers, developers, installers, operations and maintenance providers, state, federal, and international agencies, and trade associations. Some examples of the requested data that we need are the number of turbines sold domestically and internationally, the turbine model, hub height, location, and cost of newly installed wind projects, and the quantity and dollar amount of incentives that are issued to distributed wind projects. So now we'll start getting into some of the data and findings from this year's report, starting with distributed wind deployment. And it's important to keep in mind that while we call this the 2023 edition, the data actually reflects the last full calendar year. So we'll be featuring 2022 in much of our discussion today. So a total of 29.5 megawatts of distributed wind capacity was deployed across the United States in 2022. This addition brings us to 1,104 megawatts in cumulative distributed wind capacity from over 90,000 wind turbines deployed across all 50 states, the District of Columbia, Puerto Rico, the U.S. Virgin Islands, the Northern Mariana Islands, and Guam. New distributed wind projects were documented in 13 of the United States in 2022, including California on the West Coast, all the way over to New York and Virginia on the East Coast, and a variety of states in the center of the country. And the map at right shows the cumulative distributed wind capacity, and it's worth noting that the trends are pretty similar for utility scale wind energy. We see a lot of capacity in the center of the country and not so much in the southeastern part of the United States, where the wind resource tends to be lower. In 2022, Iowa, California, and Nebraska were leading the United States in new distributed wind capacity additions. And Iowa had nearly 16 megawatts that were deployed from two large-scale projects. California and Nebraska each gained a 5.6 megawatt project. The new projects in Iowa and Nebraska, the large-scale ones, are owned by utilities and are connected to load-serving distribution lines. The California project is a behind-the-meter installation for the Dole Fresh Vegetables Company. Iowa and Minnesota, located in the center of the U.S., are the top overall states for cumulative distributed wind capacity because they have a strong wind resource, active project developers, and they've received a significant number of grants over the past years. Now, focusing on small wind, where projects are using turbines with capacities of 100 kilowatts or smaller, Minnesota added the most capacity in 2022. This is largely due to EOCycle, a Canadian company that is making an effort to sell its 25 kilowatt wind turbine to farmers in its neighbor to the south, Minnesota, in order to provide a decarbonization solution for the emissions-heavy agriculture industry, which is quite prominent there. Iowa, Nevada, and Alaska are the top overall 3 states for cumulative small wind capacity, although we didn't see any new small wind deployed in 2022 in Nevada or Alaska. Now we'll move on to discussing US distributed wind projects and sales. 8 developers have accounted for nearly 70% of distributed wind capacity from projects using turbines greater than 100 kilowatts since 2018. And these developers tend to work almost exclusively in a single state or region, which I've listed out at the right, and they may not install projects every year because large-scale projects especially take a number of years to develop. For small wind turbines, sales and capacity increased in 2022, as you can see and you can see from the yellow line there that imports from non-US based manufacturers had a substantially larger presence in 2022 relative to previous years. The non-US based manufacturers that had sales in the US in 2022 were from Canada, Taiwan, Italy, Scotland, and China. Next, we'll take a look at certification of small wind turbines in the US. And currently we have 9 small wind turbines that are certified in the United States, and these range from less than 1 kilowatt in capacity to nearly 30 kilowatts. And I've included photos of some of them for you to see the different designs that we have certified in the States. We'll next take a look at distributed wind policies, incentives, and some market insights. So in 2022, the combined value of U.S. Department of Agriculture Rural Energy for America program, or REAP, grants plus state production incentives for distributed wind projects was $5 million, and these were distributed across 8 of the United States. And you can see in the bar graph that the amount of grants and incentives for distributed wind projects has been pretty consistent over the last 3 years. In 2022, over $1 million in USDA REAP grants were awarded to 12 distributed wind projects in 6 different states. And to put this into perspective, the bar graph shows the amount of grant money given to energy efficiency projects in dark green, solar projects in light green, and distributed wind projects in yellow. And you can see that wind is definitely not getting a big portion of the money here from USDA REAP. However, through the Inflation Reduction Act of 2022, the USDA REAP received a funding allocation of over $2 billion with $303 million set aside for underutilized technologies, which includes distributed wind. So perhaps this trend will be changing in the near future. Next, we'll take a look at the cost trends for distributed wind. The average installed cost for new small wind projects, which are those involving turbines less than or equal to 100 kilowatts, was $7,850 per kilowatt in 2022, which is lower than the 10-year average. So costs are coming down in the United States. They're still somewhat higher than residential solar, but we are seeing the downward trend. For projects using medium and large wind turbines, the average 10-year installed cost is $4,050 per kilowatt. And we had only one project that reported cost in this category in 2022, and that was at about $3,000 per kilowatt. All right, on to my favorite section, which is performance trends in distributed wind. If we're starting with small wind, those 100 kilowatt turbines or smaller, the average capacity factor in 2022 was 15%. The sample includes 101 turbines all across the United States, with rated capacities ranging from 2 kilowatts up to 90 kilowatts. These were installed anywhere from 2009 all the way up to the beginning of 2022. There's a lot of spread in the observed capacity factors. They range from 1% up to 37%. And I've got to say that 37% is in the range of those big utility scale wind farm capacity factors. So that's really impressive for some of these small turbines. For projects using the bigger turbines, anything greater than 100 kilowatts, the average capacity factor in 2022 was 23%, with a range of 6% up to 39%. For the distributed wind projects using turbines of all the sizes, we did a comparison of performance in 2021 versus 2022. And 60% of our projects had capacity factors that were higher in 2022. In the scatter plot at the left, projects with better 2022 performance are above that dashed 1-to-1 line, and projects that did better in 2021 are below it. And many factors, of course, go into distributed wind performance, but one of the big contributors was that 2022 was a stronger wind resource year than 2021 in the Midwest and Northeast regions of the United States. So the map at the right shows the ratio of 2022 wind speed to 2021 wind speed from ERA 5, and the warmer colors indicate where the 2022 wind resource happened to be better. Next, we'll take a look at our distributed wind market. Who are the customers in the US that are adopting distributed wind? In terms of the number of distributed wind projects installed in 2022, agricultural customers, shown in light gray, made up the majority at 33%. And this was followed by residential customers in dark blue and commercial customers in light blue, who each represented 26%. Lastly, we'll take a look at the future and wrap up with a few conclusions. Here we present our entire record of distributed wind capacity going back to 2003. And you can see that capacity peaked in 2012, and this occurred following the American Recovery and Reinvestment Act of 2009. This policy enacted Section 1603 payments, which were reimbursing eligible applicants for a portion of the cost associated with installing clean energy technologies, including wind. While the Inflation Reduction Act of 2022 doesn't provide anything equivalent to these payouts, it does provide opportunities that could benefit distributed wind, such as the dedicated USDA Rural Energy for America program budget for underutilized energy technologies, which could potentially spark significant growth in the distributed wind market over the next couple of years. Finally, much of the data that we use to create the distributed wind market report is publicly available in our newer online database, and so we encourage you to check it out and use it. We provide data on where the projects are, what the capacities and turbine models are, whether they're hybrid projects with other distributed energy technologies such as solar, and much more. And so for more information, please check out the full report or reach out to us.
Thank you very much. Is there any question from the audience? So a question from my side, do you update this report every year, or is it just now for a certain number of years that you carry out the study?
Yeah, we update it every year. It's a big effort and one that we enjoy, lots of engagement with the communities. And so, yes, we have a new report every year, and it goes back, I think this is our 11th year doing it. So the whole history is out there if you want to check out the reports, and feel free to reach out. I can easily point you to where they are, but they're all online. Yeah, and so we've got quite a history at this point.
How is it with the data collection? Is it something that takes a lot of time, takes a lot of effort, or do
I
you
think
have
you're on
already-
mute. There you go.
Sorry. So how about the data collection? Is it something that you need to suffer a lot to get the data, or is it data that you have ready available from databases?
It definitely requires some creativity and a lot of collaboration with the key players in the industry. And thankfully, it's a very nice community. People are friendly, but it's a lot of emailing, sometimes calling, getting together at the United States Distributed Wind Energy Association conference, and requesting the relevant data so that we can put it all together. So it definitely can be an involved process. I saw a question in the chat of, is it available on the NREL website? There's probably some advertisement of it on the NREL website, but it's mainly on the main U.S. Department of Energy website, and I'd be happy to drop the link in the chat.
Yes, and we can also include it in the proceedings of this conference, so that it is easily accessible, like we did for last year's report.
Wonderful, thank you so much.
Any other question? No, doesn't look so. So then, thank you very much for joining, and I hope you stay on board to hear also from the others what's happening in the small wind world. Then you might get some easier access to data in this way. So next one is Anker.
Okay. Yeah. Oh, it's working. Yeah. Hello, and now Anker here from the Folkecenter. I'm working with the data collection here and the techniques set up here at the Folkecenter. So this is just a short review what I am planning this winter to collect some extra data for, because the market is going the battery solution. And now we talk about small wind turbines. Here at the Folkecenter, we have 3 wind turbines who is connected for a grid solution. We have at the one with the tiny house, a leading edge 450 watt wind turbine who is connected directly for off-grid system. And there's a battery solution. This is a direct 24 volt charging directly on the battery, and in the tiny house there's an inverter who supply whatever they use the power for. Then we have the proven Kingspan or Ruse or whatever 2 kilowatt wind turbine who is connected for a battery system who is grid connected, and include a PV system, as Bornay was talking about, to see how much we then use the battery when we have a setup we have the boat. And then we have AC coupled directly wind turbine 3-phase, who is connected for a battery system too. Yeah. The direct couple in the straw house with PV system is quite simple. It's the most common way to do it. Is you have a DC wind turbine, 48 volt, connected for a controller, charged directly on the battery. It's a normal lead battery system, 16 kilowatt hour, I think it is, and with 2 volt cells, and automatical water filling system, and an air outlet. And there is a PV east-west system on the system who is delivery power on the DC. Then there's a Victron inverter who is supply the house with electricity or energy, and when the battery is full, it's delivery the energy for the grid, so we can use it. Here is more simple drawings how it function. The wind turbine is charged directly on the battery. The controller for the wind turbine has the features is if the inverter not take the energy and the battery voltage go more than 60 volt, then it clamp in 2.5 kilowatt load who take the wind turbine down. Instead of short circuit the wind turbine to avoid freewheeling, then it take down the RPM, so we know where we burn the energy. If we short circuit, then we can. The risk is to burn the generator, because if there come a heavy storm, now I have control over it. And then in the inverter, yes, if it's not, if the grid are gone, then it can. There's an output who can. If the battery voltage is more than 59, we burn it as heat. This system we don't directly have here. It's a PMG direct couple on the AC side, and it will be like this. But we have an achicorn, as I talk about, and I think it's I think it was Bornay who talked about when you come up in size of a wind turbine. If you have a battery PMD 48 volt, you have a limitation in current, how much energy you can take from the wind turbine on the battery side. So it can be some problem. And here we have a setup from together with Victron, who is a 3-phase system, 3 inverters, who from the wind turbine make a grid. If it's off grid, it run off grid. And I would rather take the next one to show more how it was made. The normal AC coupled wind turbine has something which is called frequency response. Has a frequency response, and that's a normal controlling system in a grid connected wind turbines today. So if the frequency go up, it go down in power, and if lower, it produce whatever it can. And the inverter has the function, normal to have the function, who is the same in the battery is full, automatically set the frequency up. And it has, if it's grid connected, then they deliver the power for the grid when the battery is full. So all own consumption will be. Here again, the same one, AC directly, to show how the inverter was. There is an output, relay output. So what I do now to the first test is only a test. I have run the first test is how it works when it's own consumption. It's grid connected wind turbine with batteries, like the one with PMD in the straw house. Here, if the grid are gone, or I disconnect the grid with 90% charge of state, then I'll run directly on the battery. And if I have not connected the heater, else there is directly in the inverter, there is, so we can connect the heater if the battery is full, or else it. The benefit, what I see, what I want to test together with Victron, is that if the DC has to charge on the battery, then the inverter has to deliver all the power through the inverter and up on the grid. If you direct couple the wind turbine on the grid, you have the consumption directly. So you not have to convert. The only thing the inverter has to do is to balance the wind turbine. And you can put PV on if you want to. And as we had talked about with the straw house, if we have sun and PV, sun and wind, and there is some consumption, we don't use the energy of the battery. So we not use the capacity of the battery. And I can see, it's quite well. And if there is no wind, then I have the same as we see when there's a load on. We use the energy in the battery in the night, and then we charge, and then we run on the battery. And we need a huge battery capacity if we have day without sun. So if we have wind turbine, we can have less battery on it. And now we have another, what I start with. The first one who was here, I have the question. What is the issue with the direct coupled wind turbine? There's different way we can talk about. There's back-to-back inverters and there's direct coupled. As the wind is very fluctuating, there is only 1 minute of data, and you can see there's very fluctuating. It's a small wind turbine, a tandem wind. When low wind, when there's wind enough, no problem. But with low wind, you see sometime when the wind is dropping to 2 meters per second, we're consuming energy. Maybe it's better to stop the wind turbine is to find a solution where it's to balance. But I have tried to disconnect the wind turbine. Then the rotor is dropping in speed. And when there is wind again, I have dropped the speed in the rotor. And then the first wind, who is coming in few seconds, need to drag the wind turbine up in speed again. And the energy I lose in the rotor, it's not worse. If I just keep the generator on and use the battery to spin it, I have the speed in the rotor, the tip speed, so I have the efficiency in the rotor. So it could be a good idea to keep it on. And this is something we have to experiment this winter when we have some wind. And as this one is the same again, I have here where there's a consumption of energy, and then I stop the wind turbine. There's a load on the wind turbine because the brake is, there's a negative brake on it, and there's a computer. I have some extra stuff in the wind turbine, so it's use a little more. And then the rotor speed come up again, and then it consume, produce. Yes. And we see the same here again. When there is no wind, here is the wind speed. When it's below 4 meters per second, there is no production. And then we dropping. Then there come a little wind, charge a little, and then the balance is. And when there suddenly comes some wind, yes, now we have charged the battery, because a wind turbine is very aggressive when there come wind. And then we think, okay, is the issue with the battery? I have to take a thermo to see where is the energy loose in an inverter system. The battery is cold, battery is no problem. The inverter, always the electronic switching, what we have had talked about before today. When you have a switching, then we can see something which is very hot. It's the controller. And it's no problem. And then the talk was, is battery storage worth it? I would say here in Denmark, maybe Norway, a different country, there will be something, the electric price go up and down. Now we have a couple of days where the electric price is zero. Then it's better just to buy the energy. And like tomorrow, I know, or was it today? It was yesterday I made it. I can see this evening, it go up to, is it more than 6 kroner per kilowatt? Then it's good to have the battery. So if there is a payback on a battery storage system in a normal household, PV, solar, we always need is a good payback on. But if the battery in itself, because of the price running, could be an investment, because the battery is dropping in price, then we are very close, because then the wind turbine is the thing you need, like Bornay talked about, to the capacity of the battery. Because if you don't have the wind turbine, then you need a huge battery capacity in the winter time.
It's something I will work on this winter. So it was only to tell about what is the I will work on here together with Victor and 3 wind turbines. And that was all what I would talk about this time.
Thank you, Anker.
Yeah.
Any question from the audience? It's after lunch.
Yeah. They are falling asleep.
So, if there are no questions, then we can move on to the next speaker. I don't know, Alexander, are you available already, or should we wait a little bit? Yeah, we cannot hear you. Sorry again. Yeah, sure. I was asking because I knew you were driving, so. But yeah. So Alexander Vallejo, it's coming from the Dominican Republic, and he's working on research at the institute specialized on high studies. That's kind of be the translation. And he has a background as mechanical engineer with a master in renewable energy technologies and a PhD in energy management for sustainable development. So then you will let us know a little bit more about Dominican Republic.
Yes, good afternoon, everyone. Thank you to this space to sharing knowledge about the smart wind energy. I am Alexander from Dominican Republic. I work in the energy sector by 10 years, academic, and by 50 years. This is our work about the key factors that influencing in the urban wind energy, applying to the case study in our country. We're talking about the introduction, wind energy assessment, strengths, weakness, opportunity, and threats factors, SWOT category, as well as the analytic and hierarchy process analysis to the prioritization of the factors, the result and discussion, and some recommendation. And the papers that we have working already and in our processes. So this is our country. The Dominican Republic is a Caribbean island in the American side. Yeah, as we know, the decarbonization is very important to achieving the sustainable development to globally, no. And in our country, we have the commitment to reduce the emission, the greenhouse gas emission, by 20% less than to the base year. And as we know, the pandemic and the conflict by the Russian and Ukraine have been some problems to our country that all fuels are imported. And the price of fuel go up 5-7 times. And we are looking for sustainable alternative to energy harnessing locally near to demand. And the renewable energy, especially the wind and PV solar technology, have grown near 16%. In the system of smart wind turbines is very low. We have 250 megawatts in net metering by PV in residential and commercial sector, but the smart wind turbine is not identified.
So our goal is to identify the potential to the smart wind turbines integrating into the building, is near to the buildings, or consider to the next architectural buildings to be then developing in the next oncoming years. And as well near to the highways and rail trains and something like that. In this map, we can see the urban energy estimation for wind harnessing purpose in the urban area is very low investigation in the tropic area. Normally in Europe and China have the most contributions. And in the right side, we can see the flow chart to the main steps by the investigation. When the characterization of the area is the first steps, wind energy assessment, wind turbine selection, annual energy estimation, and environmental evaluation and resilience assessment is very low appears in the framework of methodology that we analyze in near to 48 papers. So the environmental resilience and economic analysis are not frequently used. So as we are a Caribbean island in the tropic, we normally exposed to hurricane, tropical storm. So the resilience assessment to be in consideration the tropical storm and something like that affect our smart system. We have to be in mind the wind recovery, another process in the resilience assessment to the electrical installation. So this Anki diagram shows that the authors around the world to the 48 papers. This is from the countries. As you can see, United Kingdom have the most investigation to the urban wind energy, especially to energy harnessing in urban areas. So the Italy and China have the second most bigger country that has been reported investigation. So the country in the tropical area are very low. We can see in the tropical area, not tropical. Normally the Nordic countries have the most reported. And as well in the last column, we can see the methods adopted where the on-site measurement is the most popular, self-weather simulation as well, and numerical weather prediction or his wind atlas. And the wind tunnel and analytical methods are very low reported because the cost of the imprecision of that methods like the analytical. This diagram shows the keywords more reported in the around 9,000 papers from the Scopus, Springer, and MDPA editorials, when we can see the trends when the sustainable development and energy transition, circular economy, wind energy, urban areas are the most novel publication and hot topics now. So concerning that, this presentation, we have shown the framework to the urban energy assessment and the SWOT AHP analysis. And this is a hybridization to complement the urban wind energy traditional framework. As we know, normally the wind energy have the first 4 steps in the top of chart to the urban wind energy. When we select the site, the wind energy assessment, smart wind turbine selection according to the wind energy assessment, and the annual energy production, and something steps that are not included here by this, no was the scope of this investigation. But with the annual energy production estimation, we can calculate the levelized cost of energy and recovery time and something like that. So the application of the SWOT analysis is in order to identify the strengths, weakness, opportunity, and threats. And after that, that's our factors, our qualitative factors, we can introduce a qualitative analysis by the analytic hierarchy process with the AHP. This tool is very used to identify the priority of the all factors and the all factors identified by the interview surveys of expert group. So the AHP analysis is consist on 5 ways comparison and identify the priority of each category as S, W, O, or T. After that, the prioritization of all categories together. In the first steps, or the main 4 steps, we use the open access data from the forward. We find the most probability wind speed of 32 provinces in our country, around the urban areas in each country, where we use as well the Google map to select the positioning of the coordinate UTM code. So we use the 11 years, and the wind profile for the select country has been extrapolated by the Herman law to the city. Normally the meteorological variables are the wind speed, wind direction, relative humidity, surface pressure, precipitation. Now to the wind turbine selection, we use the vertical axis wind turbine because it's more flexible and have better performance in the urban area. As we know, the selection of the wind turbine depends mainly on the installation, height, wind speed, obviously, the aerostatic integration to the urban area. And this turbine show here have a good reported performance by Prevost in his investigation. And they have a 1 meter of diameter and sweep area of 5 meters squared. So these are good smart wind turbine with the low solidity shown in the picture. So yeah, we collect the data from the HIS open access, and we find the waveform distribution for each country, and they calculate the annual energy production by the integrating the average wind speed to the power for each wind speed, and as well the power of the kinetic energy into the electricity. In the second phase, we use the SWOT analysis as the strategic planning methods to evaluate the strengths, weakness, opportunity, and threats. The SWOT analysis is identify the key factors, the qualitative way, and the factors can be internal and external. The internal ones are the strengths and weakness, and the external ones are the opportunity and threats. This depends very important by the experience of the usement of the expert that we select. We send online survey and interview by 25 experts in the energy sector in different files in the Dominican Republic, and we get response from 20, and we clustering in 16 factors. The hierarchy, the analytic hierarchy process is a systematic technique that we can use to the priorization, to establish priorization of the factor in each category, and overall in the analysis is to establish the order of priorization to decision making. So we use normally the SATI scale to evaluate the pathways calculation. After that, we use the eigenvalue of each matrix. After that, we calculate the consistency ratio in order to identify that the consistency ratio of the pairwise comparison are very good. For a matrix 4 by 4, the consistency ratio has to be less than the 10%. So these are some equations that we establish the method, and we use the comparison by the Excel spreadsheet in order to handle the data. So some results we have in our country, 32 provinces. We have on average in the 27 identify that the margin are not good, 3.5 meters per second. When we see in the table the most potential energy in the red cycle, on average we have 3.6 meters per second. In the last column we have the kilowatt per year, 1,145. This is calculated on the average data of all provinces. This is map show the dissemination of the potential of the urban country. Normally, the most higher value have been in rural province in our country, because it's normally the urban wind energy flow and blow more in rural area. This is we have a Monte Cristi in the top on the left with the good according to this author. We have El Ceibo, Puerto Plata, La Altagracia, La Romana as identified as marginal between these steps of wind speed, and we have 27 provinces considered for wind energy potential. These are some chart because we use the calculation for each country, and this show the on average for the data on average for the whole country. When we see the wind speed, the lower wind speed is on September and October, and this information is very high correlate with the wind farm located in the most potential country from data from the wholesale electricity market. And in the right side, we can see the harnessing according to the wind energy potential with the wind speed distribution according to the wave frequency and the power in watt to the selected wind turbine. And this is some extrapolation because we have in the capital city we have some construction that grow up in the vertical civil buildings, and we can extrapolate the potential of the wind energy according to the height over the ground. And we use the on-site measurement to carry on some investigation to validate this wind energy potential. Yesterday we received 4 meteorological stations to be placed in 4 cities in our country in order to validate the data from the HIS information presented. We know the HIS information overestimate always the data, and we use the relation between both. According to the SWOT AHP analysis, we have 16 experts. We can see in the first table the position of the high professional background with 20 years of this kind of expertise. And in the second table, we can see the positive and the negative factors in internal and external condition. When the strength as identified by the expert to this kind of technology is lower greenhouse emission, availability in the urban site near to the building, possibility to the self-generation, and sales to the surplus energy, and quickness and long period recovery, sales price energy to the grid is less than the purchase price to the grid, and negative impact to the human life. It's like something the visual impact of the wildlife, negative impact to the wildlife, and the opportunity taking advantage of the public regulation and decarbonization metrics in our country, new business model to new company start up in this area, taking advantage of the incentive in the lab. And threats, we have the bureaucracy, conflict of the protected area, the resistance of the pollution, and identification of potential data by the government. This is the AHP evaluation. We can see the factor priority for each category. The category is the strength, weakness, opportunity, and risk. When we can see that the strength in overall is at 10%, and the opportunity in overall have 60%, and the quickness is 5%, and the tricks have 26%. When we can see each factor in each category. Each category have 4 factors. We can see the factor priority. We have 4 factors per category, and the overall factor we can see in the last priority according to the SATI method to the ASP prioritization. So in all cases, we have a consistency ratio below than the 10%. That is good, and per waste comparison, and the consistency of the analysis is very nice. This is a graphical representation of the last table when we can see as mentioned before, the good positive evaluation from the expert have the 69%, and the bad negative factor represent the 30%, including the internal and external. The negative are more related to the price and the payback to the investment, because the urban wind energy here is the 7 to 10 times above to the levelized cost of energy to the grid electricity. We have electricity subsidized by the government, but however the smart wind turbine depends on the wind speed locally, and we have no enough wind speed in urban area. In 2 places we have carry on site measure, and this research provide to INSA in order to establish a key strategy to the fostering the urban wind energy implementation. But we normally use the investigation of the technology. However, the investigation to the stakeholders are very important, and these techniques show some insight in light to complement the technical study of the wind energy to have a decision-making approach. The main conclusion of the investigation of the framework has to identify the urban energy potential of the entire country by his data, and after that, the identification of the factors that influence on the dissemination and systematic use of the energy is very important. So the analysis showed that on average, that over the 10 meters height open access obtained, we have four or five countries with good or marginal potential, and the predominant wind are from the north to the south. And the AHP analyzed the opportunity is the higher prioritization to indicate to the urban wind energy, and that we show that it's very positive to go in soon to certificate more strategy, because the people here are not use the law to the incentive, because the PV technology is more cheaper and it's more easy to go in. It's not rotating equipment. So in order to fostering the urban wind energy here, we thinking that these techniques for decision making can be provide insight in order to revise the regulation and provide new approach. Okay, and the number 4. Okay, in addition, we take in consideration to the hurricane in our country, we have prepared another investigation to resilience with energy system. We are presenting in this work. This paper is related to the urban wind energy resilience system, available on Sign Direct. And this is the paper that I'm showing here very quickly. The key factors. We are in the last 2 months, we went in the last 2 months presenting in the ECOS conference in Spain, the CFD simulation, CFD simulation of the building scale, and we are now submission on the on a review on the review of urban wind energy with resilient approach to the tropical city. It's something like that. This is a 2 months submission on the processing. We hope to get the publication in the coming months. Now we are working on the another paper to the RASI matrix, is to identify the accountable, is the top, the responsible, follow, the consorted, and the informed institution that be aligned and have responsibility to the urban wind energy fostering or dissemination in the urban area in our country. The matrix, the RASI matrix is very used to identify actors, and the SWOT HP analysis is very used to identify actors. No, and this is a complementary investigation that can be very provide insight to our responsibility of the institution. Those are the institutions and associations from Renewable Energy, the Ministry of Energy, Ministry of Economy, local banks and international banks, and something like that. The meteorological ministry that have to accelerate the measurement in urban area, but normally the measurement are in rural area. But those are 28 institutions related to the energy system in the smart, medium, and large scale, and our consideration to analyze to establish the responsibility and roles to each one. Thank you very much. We have open to any questions.
Yeah, thank you very much for the presentation. Is there any question? From the digital audience? Nope.
I'm sorry for my English.
No, it was perfect. Don't worry. I guess you have been clear enough if there are no questions. And you can write your mail in the chat if someone has some contact, or just if someone someone thinks of some question, then you can just write it in the chat. But thank you very much for now. So the next speaker would be Joshua Grolua. I don't know if you are ready, Joshua, because we are like 10 minutes before what we... Yeah, there you are.
All right,
so,
let me see if I can share my screen
Joshua
here.
is the CEO of Pecos Wind, and he has experience in designing and manufacturing both megawatt and kilowatt size wind turbines. He is actually also being part of designing the US tallest concrete tower, and he has also worked with ducted wind turbines. And now we'll hear a little bit more about Pecos Wind and their activities. Welcome, Joshua.
Yeah, thank you for the introduction. Thank you for the invite. Good morning and afternoon and probably evening for some folks. It's morning here, east coast of the US. That's where we're based. Company name is Pecos Wind Power. I suppose we're probably the newest entrant to the medium scale wind market, or soon to be entrant to the market. We're developing an 85 kW horizontal axis wind turbine. We've been developing this machine for a few years now. We've had great support from a few governmental agencies in the US. We've been working closely with the National Renewable Energy Lab, Department of Energy, and Department of Defense in the US. So development's going pretty well, and just wanted to give you all an introduction to what we're doing. The machine's not yet commercially available. We're still testing the machine, but we're hoping that it'll be ready for commercial sales next year. So quick summary of the machine. As I mentioned, it's an 85 kW rated power. We've optimized power generation for low wind speeds. So in the US, pretty vast wind resource, but it's at a relatively low wind speed. So at our hub height, around 37 meters, we have lots of sites that are between 5 and 6 meters per second annual average, but we have very few sites that are greater than that. So we've optimized this machine for power generation for average wind speed sites between 5 and 6 meters per second. And we do that by using a relatively large rotor. So we have a 30-meter diameter rotor, which gives us a specific power ratio of about 120 watts per meter squared. So that's very low compared to other machines. We think that's the ticket to high capacity factors and low LCOE, low levelized cost of energy. This strategy worked for utility scale wind, and we think it'll be beneficial for smaller distributed scale turbines as well. Another approach we're taking with this machine is we're trying to leverage off-the-shelf components as much as possible. You know, we realize we're a small company. We're going to be probably producing relatively small volumes at the beginning. So how do we get decent economy of scale? Well, we can use off-the-shelf components. So we're using an off-the-shelf gearbox. We're using an off-the-shelf induction generator, as many off-the-shelf bearings and other components as possible to keep costs low. And also for serviceability, we think this is important. If we want to keep these machines running for a long time, we think there's benefit to having components that our customers can order out of a catalog if they have an issue with the machine. And then another kind of approach that we're taking to the development of this turbine is we've focused quite a bit on how we can minimize balance of plant cost. For distributed wind projects like ours, the turbine itself is probably about half the cost of the project, and the other half of the cost is balance of plant. So we're talking transportation, installation, foundation, tower. So we're focused on how we can reduce these costs, and we've developed a pretty unique foundation that we think will allow us to deploy a turbine quite a bit faster. We've basically eliminated the cure time of concrete so that we can be in and out of a customer site, hopefully in a week. That's what we're targeting. So we actually just installed this foundation last week, and it was a pretty successful test run, and I've got a photo of what it looks like at the end here. So we're focused on grid-connected commercial electricity customers. So pretty typical market, from what I've been hearing throughout the presentations today. We're looking at farms, rural businesses, schools, municipalities. Initially, we're focused on the U.S. just because that's where we're located. That's the market that we know the best. We're certainly interested in international markets, but we just want to prove out the machine, and we want to prove out our business model in the U.S. first, and then expand internationally. Here's our power curve. I guess the important takeaway on this slide is that our capacity factors are pretty close to what you'd see for a utility scale machine. In 5 meters per second annual average, we're targeting a net capacity factor of low 30s. In 6 meters per second, we want to be over 40% capacity factor. And again, we do this by using such a large rotor. So as I mentioned, the machine is not yet ready. We are in the manufacturing and initial testing stages of our first turbine. What you see here, this is a photo that was taken just a few weeks ago in our contract manufacturing facility. This is our first machine. The drivetrain is almost complete. So what still needs to be assembled is the fiberglass covering and the structural frame that will support that covering. But the guts of the internals are pretty much in, and now we're starting to do some bench testing. So we're spinning up the machine, we're yawing the machine, pitching the machine, and doing some preliminary safety and function testing on the ground in our facility. We're trying to do as much testing as we can on the ground before we put the machine up on a tower. We want to minimize the challenges of fixing a turbine in the air. Here's some more manufacturing photos. The one on the left, you can see we're mounting the gearbox and the main shaft on the bed frame. The image on the right, we're mounting the hub onto the main shaft. Image on the left here, this is one of our employees standing in front of our fiberglass covering. We've got a multi-piece fiberglass covering that'll give it what I think is a pretty aesthetic look. I hope others agree with that. And then on the right, this is a photo from last week. This is the completed foundation for our prototype machine. It's a pretty unique foundation. I can't really go into details of what's underground, but we worked with the foundation designer from utility scale wind to put this design together, and the install went went quite quickly. We were able to install this foundation in just a few days. And it's ready for a turbine right now. Our turbine's not ready yet, but this is the foundation that it will be mounted on. A bit about our team. Our team has quite a bit of experience in wind, and I think we're pretty unique in that we pretty much all come from the utility scale wind space. So my background is with Siemens Wind Power. Our head of engineering is from Vestas, and pretty much all of us cut our teeth either in the design, manufacture, or testing of large-scale turbines. And I think we learned a lot about how the industry works over those years. And now we're trying to take kind of lessons learned from utility-scale wind and scale them down to our smaller 85 kW machine, with the whole goal of minimizing cost of energy from our turbine. And as I mentioned, the machine's not yet ready for sales. We're still in testing stages. We're hoping to deploy our turbine on a tower and do proper field testing this fall. So by the end of the year, we're hoping to have blades spinning. And we'll certainly take some photos and videos and post that online. And if testing goes well, we're hoping to pursue certification testing next year and in parallel start first commercial projects. We've got a handful of pilot customers lined up in the US, so we'll start deploying those probably second half of next year if all goes well. So my contact information is here, and you know, we're a pretty young, flexible, nimble company, so we're always looking for collaboration or partnerships. So if anyone on the call is interested in what we're doing, please don't hesitate to give me a call or shoot me an email. And it'd be great to connect with more international folks, because right now we're pretty focused on the US, and we'd like to open our doors a little bit and see what's out there internationally. So that's all I got, but happy to answer any questions.
Yeah. Thank you very much for the presentation. I think you should try to look back at the presentations of this morning and see the presentation from Otto Reinke, because that's a lot of the things are going in the same direction, so there might be a collaboration coming in there.
Great.
Yes, exactly. So is there any question from the audience? And of course, if you need any testing facility in Europe, yeah, Folkecenter is available. Should do some promotion as well.
Good. Thank you.
So is there any question? No? So thank you very much, Joshua. And yeah, should any question appear, then they can just write to you. So if you can put your contacts in the chat, then of course we will share the slides, but that takes time. Then in this way we cut the curves. Now we will move to Brent. Are you online? Are you ready? I think I saw him. Yeah, there he is. So, good morning, Brent. So Brent Somerville, he has worked a lot with distributed wind energy and with standard developments. He has both technical and academic experience on the field, and since 2020 he is part of the NREL, National Renewable Energy Lab. He's also a member of the Task 41 from EIA, and he's in charge of the update of the DASH2 standards. Yeah, I will not say more about your work. That's I leave it to you. And I can see a very nice picture of Folkecenter. You and Folkecenter there.
Yes,
So,
yes, great to
floor
be
is
here.
yours.
Thank you, Danielle.
Welcome.
All right, thanks everyone. I think I'm the final speaker today, so hope you had Hope you've had a great day of presentations. I was able to catch the last few after getting the kids off to school here today. But yeah, it's great to be here. Fond memories of my visit to the Folkecenter in 2019 with my wife. Beautiful spot. Really enjoyed our stay. The presentation on the battery charging wind turbine was great. I slept in a little passive house right next to that Proven, I think 2.5 kilowatt machine, and it was always going from the breezes coming in from the fjord. Anyway, thanks for having me. I thought I would give you a quick update on where we are with the update to the small wind turbine standard IEC 61400-2. So the current -2 standard was went through the 3rd revision from about, I think, 2009, 10, 11, 12, and then at the end of 13, it was released, and edition 3 is still out there. Currently applies to electricity producing wind turbines up to a rotor swept area of 200 square meters. And, you know, the old days, that could have been a 65 kilowatt machine, but with modern trends of lower specific power, 200 square meter rotor is what we see in the 20, 25, 30 kilowatt EO cycle S16. And the standard covers design, engineering, and some testing of small wind turbines, including duration test, safety and function test to achieve design data like RPM and power. And then, but other testing requirements, as you know, are in other standards such as power performance and acoustic testing. -2 is being used all over the world. In the US, our ACP 101-1 standard points you to the -2 standard and makes a few changes to optimize and streamline things. Japan points to it from their small wind turbine standard, the UK, Denmark, all over Europe, and the overarching scheme of the IEC RE small wind turbine type certification falls under their operational document OD 554-1, and it, of course, relies heavily on the -2 standard. We have about 35 global experts in the small distributed wind field participating in MT2 right now, and the 4th revision is officially underway and has kicked off in May of this year. And just to educate you, if you don't know, IEC is the International Electrotechnical Commission, overall a huge suite of standards. TC88 is the technical committee focused on wind energy standards, and MT2 is the maintenance team for the -2 standards. So, for instance, the -1 turbine standard is under revision, and that is being shepherded or performed by MT1. Okay. So stability date, you know, after releasing the standard in 2013, which I was a part of that revision cycle and very much enjoyed that process. The stability date by default puts it out 5 years to be stable and not revised, and that was through 2018. And then that was, you know, it was a bit of a slow adoption of the standard. Takes a while to transition from the previous editions to the latest. So the stability date was extended to through 2021. And then the experts were polled and the then convener David Sharman in the UK and MT2 decided to extend it again through 2025 to allow various work projects to complete, such as some of the IEA wind task research that had some outcomes directly helpful for this revision. So now the standard out there now is stable through 2025, but the revision for the 4th revision has begun. MT2 has been meeting virtually since May of 2022. And we call this preparatory work. And it took us quite a while, but we went through meetings to establish a scope of work for this fourth revision. So you have to propose to TC88 what your group plans to do to the standard, and then they approve this scope of work. Almost all of the meetings have been virtual, monthly meetings. We did hold one hybrid meeting in March of 2023 in Arlington, Virginia, near Washington, D.C., following the Distributed Wind Energy Association Conference, DWEA 2023. And everyone's important here. But I do want to point out Joe Sposi is our secretary, which is a critical role in standards development. Much appreciated there. Some of the folks were in the room, and some of the folks were participating virtually. So I would say this was a successful annual hybrid meeting. The virtual meetings are about 2 hours long, and it's a chance for us to discuss things as a group, but not a lot of work gets done in that short amount of time. This hybrid meeting lasted for a day and a half, and we were really able to go through lots of topics and deliberate and have guest presentations. So we're going to try to continue the trend of holding about an annual hybrid meeting. Okay, so MT2 says, you know what, we're going to go through the whole standard. There are no portions of the standard that are off limits. We did some polling, and we wanted to work on improvements to air elastic modeling, including the tools available for vertical axis wind turbines. Simplify or clarify the load testing requirements used for model validation. We wanted to, based on recommendations from the international community, have another look at the scope of -2 at 200 square meters. It was seen as this was too small and was a barrier and was leaving out small turbines that should fall under our standard, presenting a barrier to market entry. Duration tests, optimization, we really took a pretty hard trim on the duration test requirements in the US ACP standard to reduce the cost and time for that test. Look at all the safety factors, simplified load methodology, turbulence, blade testing, clarify safety and function testing, look at our modal analysis of tower and turbine dynamics, update the title of the group, look at the HAWT simplified load methodology in the Japanese standard, look at the inclusivity of the standard to all turbine types, and so think about novel designs, and clarify protection and shutdown systems, go through the electrical section, what can we learn from -1 to make -2 a better standard, and so on. But really the key issue here was redefining the upper scope limit of -2. That became quite a discussion. It almost put us into what we call an existential crisis. The group says, okay, what is a small wind turbine? We are in charge of revising the small wind turbine standard. We're hearing from IEA Task 41, a global group of wind experts, that this scope is too small. So we looked around, -2 was setting small wind at 200 square meters. As I said before, that's like about 20-25 kilowatts these days. Brazil, 100 kilowatts. ACP 101, we said small wind was up to 150 kilowatts. And the European Academy of Wind Energy stated that many problems and technical challenges of small wind turbines are common to the majority of rotors, up to about 500 kilowatts. So we took this from the current the small wind turbine grand challenges, which you'll hear about tomorrow from Alessandro. This little statement provided a hypothesis. Unlike the typical utility scale 3-bladed upwind, full scale pitch active yaw machines, small wind turbines have not coalesced into a dominant archetype. with many different layouts still being offered on the market. So, we've got a variety of HAWTs, upwind, downwind, tail, active yaw, coning, blade pitching, two-blade. We've got vertical axis wind turbines. We've got diffuser augmented wind turbines, and possibly even airborne wind. So lots of archetypes fall within the smaller end of the scale of wind turbines. So we did a bit of analysis here and tried to have a look at what the archetypes were for all, not all, but a very wide range of turbine sizes. And flagged each of these dots as an actual turbine with a rotor swept area and a rated power and an archetype. And so, as we can see, the vast majority of large wind turbines fall under the same archetype: 3-blade, horizontal axis, active yaw, upwind, active pitch. But down here in the smaller end, the hypothesis is small wind is smaller, so down here somewhere, and has a variety of archetypes. And way down here is the current small wind turbine group, and then the current medium wind is defined in the -1 standard as 200 to 1,000 square meters, so this little group. We zoom in on those, we see, okay, here's the current definition in -2 of a small wind turbine. Some older machines have high specific power and or up above 50 kilowatts, but the trend of lower specific power, which I've drawn just through the Pecos machine that you just heard about, which I think was 120 watts per square meter, then that puts a modern 200 square meter turbine, as I said before, about 20 kilowatts. And so we've got this group of small wind turbines now, but we're thinking, what about this group that's just right there with them? In the US, we called small wind everything under 150 kilowatts to capture these roughly 100 kilowatt machines. And we look way out here at 700 square meters of swept area, and we see an 85 kilowatt machine. Now, is this a small wind turbine, or is this a multi-megawatt wind turbine? So, many discussions around this. We also said, well, these archetypes of, say, passive yaw go all the way out here to the Carter 2-blade downwind machine, which has 1,052 square meters. So that forced us to look up in the 1,000 square meter range, knowing that -1 is defining medium wind as 200 to 1,000, capturing these turbines. And ultimately decided that this dot, represented by the Carter, is the largest small wind turbine known, and set a upper limit of 1,200 square meters of rotor swept area as the new definition in our standard of small wind. It's not that clean in that we've also proposed 3 subcategories within the -2 standard. So a new size category would be micro wind, up to 5 square meters of swept area. So these are turbines of about 1 kilowatt and below. And small is sort of like the old -2 definition, 5 square meters to 200 square meters. So very much in line with the existing -2 scope. But then we've added a new category called medium of 200 square meters to 1,200 square meters. And we discussed this with the MT1 in charge of the -1 standard. They are okay with moving the medium wind NX from -1 into -2. So we're providing this group of turbines basically with a new home. They fit pretty well within the -1 standard that does apply to all wind turbines, but it's pretty well known that that standard is focused on the needs of very large multi-megawatt turbines, and is probably not very interested in the needs and certification, testing, and design of a 30, 50, 100 kilowatt machine, which is much smaller. We had pretty good agreement around the globe on doing this, but the Great Britain National Committee did have some interesting deliberations where they were pretty unsatisfied with the technical rationale of increasing the scope, but ultimately decided that they were no longer actively opposed and just let it move forward to see what happens. So we presented all this to TC88 in April, and they agreed to allow us to move forward with this new scope, and we kicked off the 4th revision on 18 May of 2023. So our hope is to have a new standard in place half a year or so after the stability date, sometime in the spring of 2026. That means that we need a committee draft by a year from this November. So we've got quite a bit of work to do, and then we'll move it through comments and voting and the final standard. Some of the research needs in the MT2 include, some designs of a turbine under the simplified load methodology versus air elastic modeling, comparing the loads and the impact of the high safety factors there. Much like the work that was done by Davide at DTU a few years ago, or started. We're collecting common materials used in small wind turbine design. So if you have some input there, reach out to me. Turbulence, now that we have a larger group of turbines within our standard, we want to make sure that we have the appropriate turbulence assumptions in there. And in fact, at today's MT2 meeting this evening, we're hearing from a historical perspective of turbulence research from Neil Kelly, who has been doing research on turbulence since the 1980s. Very much interested in getting data on yaw rate and yaw behavior for passive yaw turbines so that we could better inform those design elements. And we want to set forth some minimum load measurements for air elastic model validation in the standard. So we're looking for any research related to model validation. Here at NREL, we're attacking some of these. We're installing these 3 turbines right now at our research facility in the US, representing the top 3 dominant archetypes of distributed wind. Represented by the Berge XL15, passive yaw stall regulated with a tail, and the EOCycle M26, previously Zant from Belgium, a stall regulated downwind passive yaw, and then the QED Phoenix, which is an upwind stall regulated active yaw machine. And we're building reference turbines for each of these, which will provide a model template and a basis for research into these archetypes, collecting data from field experiments to validate the model. And we've also been doing lots of code improvements to the OpenFast air elastic modeling code, bringing back tail vane modeling, improving yaw friction, and automating the generation of Campbell diagrams for modal analysis. We've also reinstalled our Pika T701 turbine, another passive yaw machine with a tail, to further validate our tail vane modeling capabilities and OpenFast. And we're using data from industry partner Xflow Energy, who has installed their prototype 25 kilowatt vertical axis turbine at the Windward Engineering Test Site in Utah. And that data will be used to help validate new tools for the modeling of vertical axis wind turbines, something that we're collaborating with Sandia National Laboratories on, and are spending two full years to improve VOT modeling codes. Provided a link in the presentation to this DWAM project, which is focused on distributed wind air elastic modeling. But if you have any research related to small wind turbine design, testing, field experiments with data, we welcome this into the group to improve the standards. So that's all I have for now. The hard part here is getting the work done virtually. Much of the work has to be done in small groups outside of our regular virtual meetings, and that can be difficult to coordinate. Everyone's very busy, but we have a great team working on it. I put this picture up because our president of the U.S. visited NREL, and in the background are our row 1 small wind turbines back here, which will be the new home of these new distributed wind turbines. This North Wind 100A will come out. It's been there since 2001, and we'll see a whole new array of distributed wind turbines at our test site this fall, happening right now. Okay, well, thank you very much for having me, and it's a pleasure to be here.
Thank you very much, Brent. It's actually a very nice picture. It gives hope for the near future.
That's right.
Do we have any question from physical or virtual audience?
Perhaps I can raise a question?
Yeah, hi Sven, good to see you. Sven was very helpful in this third revision of the -2 standard, so thanks a lot.
Hi, Brent. The same. It was very nice to see you here, and I'm impressed by the work you have started, and the new scope of including turbines up to 1,200 square meters sounds really interesting and challenging.
Yeah. Yeah, it does. Go ahead.
Yeah, what I wanted to ask is, I have not been following that field lately, but is there now any simplified path for any of those turbines above the 200 square meter limit, which you sort of have to consider if you're now making a transition to including it in the -2, or are they bound to follow the -1?
That's a great question. They are bound to not follow -1, but they are bound to use air elastic model simulation for the basis of their loads in their design. The simplified load model would not extend up into that medium wind category. So yeah, much of the work in -1 we're hoping to use to inform an improved suite of design load cases and safety factors and other helpful information in the -2 standard. So I don't know if we're going to directly say, okay, if you're fall under -2, you're in the medium category, use -1, but we are hoping to incorporate a lot of the -1 elements into -2, because as you know, we already have a pretty good set of design load cases and assumptions. We just want to make sure they're fit for this new larger size.
Yes, perhaps I didn't express it so clearly, but I was wondering, is there any simplified approach about 200 square meters today, which I'm not really aware of?
No, there's not. There's only air elastic model simulation and not a simplified load methodology for that size category.
Mm-hmm. Because I know already, some 10 years ago or so, there was talk about the need for a simplified approach for them, but we couldn't find a way, at least during the time I was involved. But I actually thought there had been something there, but then there is nothing you sort of need to consider, which has become like a de facto standard or so.
Right. Yeah, we're planning to incrementally improve the simplified load methodology, but it will still only apply to the smaller turbines and not to the 200 to 1,200 square meter range. I think the safety factors are too conservative for that turbine to be economically feasible using a simplified approach. So therefore, to get an optimized design that will be competitive, reliable, then the only real option is to use air elastic modeling codes.
So there has not been like a US or any other national standard which went above 200 square meter for medium size
or a simplified loads calculation approach? Not that I know of.
But with any other approach?
The only other approach is well, currently that 200 to 1,000 square meters falls within the medium wind NX and -1, where they say do the -1 except assume a higher turbulence and a few other minor modifications. But And so that's still an option because -1 applies to all scales of wind turbines. So if you have a 500 square meter rotor swept area, once this standard comes out, you'll have options. You can go the -2 route, or you can go the -1 route, whichever serves your needs best. But our goal is to serve the needs of this smaller group of turbines within our standards, so that they're not forced to set at the -1 table, which may not fit the needs of their turbine size.
Thank you very much for clarifying it. Then
Thank you, Sven.
We understand a bit more why there is a need for this, and good luck with that.
Thank you very much.
Thanks. So, is there any more question? No. Then I would like to thank Brent and all the speakers that have been on today. Thank you very much to join with also with very short notice in some cases. So tomorrow, this was the last presentation for today, and tomorrow we'll start again at 9, and then we'll continue up to around midday, roughly. Yeah. So then I would like to wish you a good day and see you tomorrow. Thanks for joining.